Hello, everyone, and welcome to the inaugural Causal Inference Symposium, which is organized and hosted by BP. My name is Franziska Bell, and I'm the Senior Vice President for Digital Technology at BP. And I'm so excited that you have joined us today, and I'm honored by the large number of peers and pioneers that have volunteered their time to speak with all of us. Now, more than 2,000 people from over 1,000 companies and academic institutes registered to attend today, and it really means a lot to see our causal community coming together to share our findings and explore new ideas. Now, needless to say, artificial intelligence has taken the world by storm. Users, employees, and also companies have truly benefited from its applications. And data science has now become an integral part of our everyday lives, whether it's content recommendation, maps routing, or machine language translation. And also, of course, at BP, we have been using AI and data science to help accelerate BP towards its net zero ambition, provide improved user experiences, and also support safety. We have a global data science team, and they do their work heavily committed to using these technologies purposefully as well as also safely. At BP, we use AI and advanced data science across all of our businesses. For example, we're using data science to help us choose the best sites for EV charging points, green hydrogen, as well as wind farms. We have a team that is part of our BP's incubation business called Merge, and that leverages generative AI to provide code reviews as a service. This helps software developers to code safer at scale and delivers average productivity gains of 20%. AI is also helping us keep our people and customers safe. For example, supporting the prevention of accidents and stoppages, whether it's in field, wind farms, solar farms, or even in airfields. And in airfields, we're using our award-winning Safe2Go mobile application that uses computer vision to match aircraft decals to the correct fuel type and really helps making refueling safer in more than 600 sites in over 40 countries. Now, these are just a few examples of where AI has been supporting our work. And as we all know, whilst traditional AI has unlocked benefits, it also does so using correlation and really has no sense of cause and effect. And this can really lead to significant failures of these correlational models. So incorporating domain expertise and developing models that capture cause and effect is absolutely vital, especially in high-stakes decision-making, such as, for example, in the fields of healthcare, economics, and also self-driving. And I personally believe that the lack of cause and effect in these models today is the biggest blocker for artificial intelligence being able to reason and attain human-level intelligence. So why is BP hosting this event? Despite its criticality and potential, causal artificial intelligence is not yet getting as much traction and attention as it deserves. Only a handful of experts are talking about it, compared, for example, to areas such as generative AI. My team and I feel that causal inference can have large impact across many different industries as well as fields. And so this really prompted the idea for this symposium. And our aim with this annual symposium is to build a community around the topic, to bring great minds together and to solve problems that truly matter. Now, a little bit about today's session. We have a phenomenal lineup of technical experts who will be sharing examples of how causal inference can unlock opportunities and create value. And I'm really grateful to all of you for your time, and I can't wait to learn from you. Now, I encourage everyone to also join our panel discussion at the end of the day, when my colleague Harsha Tharkabhushanam, who is BP's head of data science and artificial intelligence, will be exploring how we can use causal techniques across organizations to unlock new opportunities and value. And he is going to be joined by Lars Kunze, as well as Candice Hogan in this conversation. Now, before we get started, a couple of items around hygiene and guidelines for the event. Our speakers are live today, and they're happy to answer your questions. Please type any technical queries into the box, and the speaker will receive them. Should we be running out of time to address your questions, please email them to the team at energyai@bp.com, energyai all together. and we will forward it to the relevant speaker. Now, needless to say, our speakers won't be sharing any confidential information about the companies they work for or projects that they're working on. This is really a space for us as practitioners to swap ideas, solutions, as well as challenges. Now, as part of our commitment to building a causal AI community, the team and speakers have very carefully tailored this event to causal AI practitioners. As such, the speakers will be prioritizing questions that are technical in nature and help move causal inference from theory into practice. Now, they're very excited to share their technical expertise with you and to help, of course, remove any blockers and make causal inference much more accessible. You should also know that recordings of these sessions will be available, and they will be available on the portal for about 2 weeks after the event. So if you need to go to a meeting or get a cup of coffee and take a break, don't worry, we've got you covered, and you can catch up later. Now, with that, I'm going to hand it over to our brilliant moderator and staff data scientist, Natalia Konstantinova, and I look forward to connecting with you throughout the day. Now, thanks again for joining us, and let's get started.
So Judea was talking about causal inference in the context of experimentation mostly. But of course, one of his many kind of original contributions was to kind of show how data together with assumptions can be used to estimate causal effects. And in my talk, I kind of want to go back to that idea and really kind of highlight, or maybe to kind of try to convince you that we should kind of go back to that basic idea and really think hard about assumptions in causal inference. So to kind of see what I'm talking about, it's useful to think about all these kind of estimation methods that have kind of been developed in the past couple of years. From depending on the timeline, but certainly there's been a kind of boom in these different kinds of estimation methods in the recent years. We know a lot of these kind of like propensity score matching, double machine learning, policy optimization methods, double robustness. These are kind of familiar buzzwords for anyone who's kind of focused or paid attention to causal inference in the past couple of years. And what is common between all of these various methods? Well, what is common between them is that they all rely on assumptions. So these methods on the previous slide are ones that we know will give you a treatment effect estimate that is unbiased, given that your assumptions that you make about the causal scenario are correct. So to take one of the common examples, like propensity score matching, if you calculate your propensity scores in such a way that you have added all the confounding variables, then you will have an unbiased treatment effect estimate. And similarly, for all of these different methods, they kind of all have their own assumptions, which are slightly different, but the idea and the common factor is that they all rely on those assumptions that we make. And from this perspective, I think what's happened in the past couple of years, especially as causal inference has become very kind of hot topic, is that we have kind of put the cart before the horse, in the sense that there is a lot of kind of development, if you look at the literature and also practical applications around these estimation methods, around these different methods that allow you to derive an unbiased treatment effect estimate given assumptions. But actually, there is very little work on what constitutes a good causal assumption, what gives you a justified causal assumption. So a lot of kind of papers and, as I said, like a lot of content on this estimation part, but actually not a lot of work on the assumption side. And, if we take this iceberg metaphor, that's an issue, because the assumptions are actually much more important than specific estimation methods, because all of these estimation methods, they will do nothing for you if your assumptions that you make are not correct. So maybe to kind of like, I've now kind of done the iceberg and the cart before the horse, so maybe one more kind of well-known metaphor here. So kind of, in my view, looking at kind of like these estimation methods rather than what kind of assumptions we should make is a little bit like shuffling the chairs on the deck of Titanic. I think, yeah, as I've kind of said, like the most of the work happens at the level of the assumptions rather than the estimation methods. So this is just kind of like one additional metaphor to throw in here. And from now on, I promise I will not return to these icebergs and Titanics and horses and whatnot. So let's instead talk about an example. So here's a very common kind of inference task that inference data scientists would be doing. What is the effect of experiencing a bug on future engagement with an app? And so data scientists know that it's not a good idea to just compare those individuals, those customers who experienced the bug and those who didn't, because those groups will have very different engagement levels. So those people who were already engaged in the past, they will have a much more higher probability to experience a bug. And now if we do this comparison, we get the counterintuitive result that actually if you have experienced a bug, you are likely to have higher future engagement. This is just caused by the pre-existing difference between these two groups. So all data scientists nowadays kind of can appreciate this result. And so imagine there is a kind of meeting among data scientists to kind of talk about this problem, like what we should do in this kind of situation. Well, the first idea that comes to mind to one of the data scientists in the meeting is that, well, we need to condition on past engagement with the app. We need to kind of reduce the bias between these two groups and do the estimation of this effect of experience about by doing that. And everyone agrees this is a great idea. Very kind of clean model here. We just run a regression model with all these three variables, and we look at the coefficient for the indicator for experience the bug. But then one of the data scientists points out, well, actually, maybe also location is relevant for this relationship. So maybe we should add that variable into our model too. Everyone agrees, great idea. Again, and this data scientist is happy because now the variable that he or she proposed is also included in our multiple regression. But then there is a third data scientist who stands up and kind of like points out that, hey, what about the number of past purchases? This seems important too. Again, everyone agrees. And now we have a third model here. Is this already a fourth one? Then the next data scientist points out that, well, but also there is this question of whether these individuals received a promotion last week. And now we have the fifth model, everyone agrees. And then this starts to be kind of like a big meeting. And now there are like, this is maybe like the eighth data scientist, and they point out that actually these variables are related with each other in all kinds of interesting ways. And potentially we need to take this into account when we come up with our model. And so now we already have four models, and this process, of course, could just go on and on forever. We might end up with something like this. So this is actually a group of experts, I think, in the UK. They were asked to come up with a causal graph of the causes of obesity, and they came up with something pretty complex. And this is a typical scenario, because when you start thinking about concrete kind of real problems, this is often what happens. You kind of start to appreciate the complex nature of reality. And the point here, and the kind of worrying thing here, is that all of these different models, like anything starting from this like super simple model with just two variables to this kind of monstrosity, they are all potential models that we could use to fit, do our treatment effect estimation. And probably all of those models will give slightly different estimates of that treatment effect. So this is the issue. How do we kind of decide which variables we should include in the model? And now, apologies to Judea again. I'm kind of going to adopt this idea of a ladder. This is nothing to do with the ladder of causation. We'll introduce another ladder, never too many ladders, which is about the ladder of assumptions. So at the lowest rung here, we have hidden assumptions. So we're not even talking about the assumptions. We're not making clear what they are. At the second rung, which is slightly better, we have explicit assumptions. And maybe this is a causal model, like we can at least see what the assumptions are. And then at the highest level, we have justified assumptions, not only explicit assumptions, not only kind of like describing clearly what the assumptions are that we make, but actually justifying, trying to kind of like, yeah, give a reason for those assumptions. And I think like, you can think about assumptions in this way. Okay, I want to address some frequently asked questions immediately. The first one is, can we just only do experiments? Because all this stuff about making these assumptions is problematic to some people, and they would rather avoid this whole thing. And for various reasons, experimentation is the way to do that. So you don't need to kind of worry about these backdoor paths and these confounding relationships if one of your variables, if the variable of interest is a randomized experiment. There are variations of this argument, but this is the basic idea. And the answer to this commonly asked question is yes, we can rely on experiments in limited scenarios. The limited scenarios are ones where we can actually manipulate the variable of interest and where we can measure the short-term, mostly short-term effects of that change. So if you go back to the example of the experience of bug, this would mean that we would randomly need to assign bugs to people who use the app and to measure its impact by doing that. And the issue, of course, is that many times we don't want to do this. And these are kind of well-known arguments. I will not rehearse those. So randomized experiments, they are great in their specific context, but often that context is not the one that we are interested in as inference scientists, because we want to answer these difficult questions. I will skip this slide in the interest of time. The answer is no. If you're interested, if you want reasons, send an email to me. The second important kind of question that is being asked in this context is, can we just use an algorithm to learn the true causal graph? Basically, this is the idea of kind of looking at the kind of conditional independence relationships that exist in observational data when it has these causal relationships, and we might have an algorithm that could learn these and could kind of free us from this task of coming up with the graph. Unfortunately, this is not possible for practical reasons, and I guess for theoretical ones as well. The practical reason is that it doesn't work with any reasonable data sizes of data at the moment. So you're usually limited to like some thousands of rows, whereas usually in the industry you're dealing with millions, hundreds of millions, or billions of rows. The second reason it doesn't work is that the results are often nonsense if you're able to apply these algorithms to begin with. So this is a promising idea, but it's nowhere near helping us to deal with this problem in practice. Okay, can't we just rely on a subject matter expert? This is the last question that I will want to answer here. And here the answer is yes, we can rely on a subject matter expert. However, this subject matter expert is a kind of fluid or mythical character. And I imagine it kind of, based on what I've seen in the industry, it operates something as follows. They enter the room, reveal the true causal graph, refuse to elaborate any further, are never to be seen again. So you often hear that a graph has been formed or causal assumptions have been formed with the help of a subject matter expert. However, my suspicion is that often the subject matter expert is actually the data scientists themselves, or someone who has a kind of vague idea of how this particular problem might work in the context of a business or organization, or I guess like policy and those kinds of things. So yes, we can and should rely on subject matter experts, but this concept needs to be defined. Which brings me to kind of like the positive part of this talk. How can we move towards justified causal assumptions? Well, firstly, we need to define what is or who is a subject matter expert. Who are the people that we should include in the discussion of which causal assumptions make sense. It can't be just the people who happen to be in the room. There need to be some criteria, which might vary from organization to organization, or across different literatures, or across different contexts. But there should be some kind of shared idea of who are actually the people who should be involved in the discussion about the causal assumptions that we should make. What do we do? And this is the second kind of question or element of moving towards such assumptions. What do we do when there's a disagreement between these experts that we have collected in the same room? Because it's not reasonable to assume that the expert will just agree on everything. What do we do in those kinds of situations? And we need some principles. Again, these probably vary from context to context. What is the degree of evidence required for us to make a causal assumption, which is this kind of assumption that one variable causes another? When are we licensed to draw one of these arrows in these causal graphs that I just showed? The strictest kind of requirement is that there needs to be a randomized experiment for each of these arrows. That is too strict and impractical because of the issues that I talked about in the context of randomized experiments. And the loosest criterion is that someone said so in a meeting. And so we need to land, I guess, somewhere in between these two. And again, this can vary between contexts. And finally, moving towards justified assumptions requires describing them. So using these, and I think the best tool here is the causal graph, because it's very transparent. It shows those assumptions. And the benefit is that it can also be shared across organizations, and it should be shared across organizations so that different kind of stakeholders can verify the assumptions, can suggest their assumptions. And by using these other criteria that I talked about, it's possible to come up with a shared causal graph across an organization, for example. As far as I know, no organization is here yet, but I think it's something that we should be doing if we want to elevate the practice of causal inference as we do it today. So this brings me to my conclusion, which is that describing and justifying assumptions is actually the most important step in practical causal inference, because as I said, different assumptions, different results. And before we kind of talk about all these estimation methods, we should actually find our answer as practitioners and as different organizations to the following fundamental question: what is a justified causal assumption? And we should have these criteria that, again, can vary from context to context so that everyone can agree on those across organization or whatever the relevant context is. Thank you.
Thanks a lot for a great presentation. I'm sure everyone enjoyed. And you made me smile at several points when you mentioned this professional that enters, checks the graph and goes away. Quite aware of the situation. So I have a couple of questions, and please, audience, bear with me. I have several devices to read things. So the first one is, obviously, you're saying that it's extremely important to have these justified assumptions. So why do you think there are not many tools to do this? And even the term, I haven't seen it so much in the literature.
Yeah, so I think it's true. I don't think there is a lot of discussion of what counts as a justified causal assumption. And I think there is a universal kind of recognition that causal inference does rely on assumptions. So that is good. And it's a bit of a mystery why it's then the case that we don't have tools for it. I think it's to do with the fact that ultimately coming up with these assumptions is kind of, there's a qualitative element to it. And also related to, I guess, that qualitative element is that it's difficult to evaluate when you have done it properly. So if you just think about from a practical point of view, I guess if you are developing an estimation method for some treatment effect, you can maybe simulate data and you can kind of evaluate your method against that. Whereas with coming up with justified assumptions, it really depends on what the reality is. And often in these situations where we do causal inference, we don't really know. So there isn't a clear kind of yardstick against which to evaluate if your tools or criteria or or whatever you come up with actually match the reality. So I think that it's this kind of qualitative element that kind of makes it so that it's not particularly interesting for data scientists and the researchers working in this area, which is a shame because, as I said, I think it's fundamentally important.
I can see how passionate you're about causal inference. So can you tell me, we have a next talk and it's about LLMs. How do you preach causal inference when you have all the hype around generative AI happening? Did you feel it then?
I look forward to Robert's talk. I think I think actually like some of these questions that I raised and kind of talked about, especially like around elicitation of these assumptions. I understand that his talk is actually kind of also around those kinds of questions, and actually see a lot of potential synergy there. For example, I know that many organizations are kind of hoping to incorporate their internal documentation, for example, in such a way that you could query it using a chatbot. And I think that could be one way. I can't see why you couldn't kind of like start incorporating this kind of causal information that I talked about and kind of like use chatbots as a tool to kind of like come up with these organization-wide shared assumptions. So I see there's a huge potential there. So yeah, I guess I look forward to Robert's talk. I hope he'll kind of touch on some of these questions.
Yeah, everyone liked Invisible SME, by the way. So we have comments coming, so everyone can relate to this. I think you mentioned actually on the talk saying that you believe that discovering causal graph just from data is not really possible and feasible. Yeah.
Yeah. I mean, I guess like what I'm saying more is it's not practical at the moment. So my kind of the way in which I do is that I every kind of 2 years, and these kind of graph learning methods have been around, I think, from '94 or something like that, where the first papers came out. And so every 2 years, I kind of like take a practical observational data set from my work and apply these methods, like whatever is the cutting edge at that point. And I'm always disappointed. So I think it's like it's a practical question of like the computational time, but also it's also about the results and how much they make sense or don't make sense. So I don't want to kind of argue that it's never possible to come up with a great algorithm for learning these relationships, but I think it's like I haven't seen it, and I don't think we're particularly close. So like if it takes 20 years to come up with that, then I think like in the meanwhile we still need to rely on these subject matter experts and figure out like how we can extract their knowledge into a graph and do that in a principled way.
So as we have more speakers lined up, brilliant ones. So we have some more questions. So I think Totte was saying that he can answer. So I don't know, you can find him on LinkedIn and send his questions, or we will try to collect all of them and send across to our speakers who might agree to answer them in a blog post afterwards. We can't promise anything. I haven't done any promises here. So thanks a lot for joining us.
Hi, everyone. Thanks for having me. My name is Jeong-Yoon Lee. I'm a senior manager in the marketing applied science team at Uber. I'm one of the main maintainer of the Causal ML open source project, along with our earlier presenter, Totte Harinen. Today, I'll present about Causal ML in practice. We will start with a brief introduction to Causal ML, and I will introduce various Causal ML methods and open source tools. And finally, I will share a couple of Causal ML use cases. Let's get started. So first, why do we need Causal ML while we have ML? ML is extremely good at finding associations between, let me check. Well, I don't think I can change it right now. Yes, sorry about the erasure. Let me go ahead. So again, ML is not formulated to answer causal questions, and is susceptible to spurious correlation. And here are some examples of spurious correlations. The first chart at the top shows a high correlation between US spending on science, space, and technology versus suicides by hanging, strangulation, and suffocation. And the second chart below shows a high correlation between Japanese passenger cars sold in the United States versus suicide caused by motor vehicle crashes. ML algorithm can quickly discover this kind of association from the data with thousands and millions of variables, but it can't be used to infer their causal relationship. So Prosperi and coworkers noted data-driven prediction models are often mistakenly used to draw causal effects, but their parameters nor their predictions necessarily have a causal interpretation. Then how can we estimate causal effect in general? Suppose we'd like to estimate the causal effects of treatment T, like marketing email, on outcome Y, like user's order. Besides marketing email, confounders X, such as users' demographics and previous order history, might affect the user's probability of placing an order, as well as the probability of getting the treatment. We can most commonly perform a randomized controlled trial, or RCT, which removes the effect of a confounders X on the treatment T by random treatment assignment and estimate the average treatment effect, or ATE. When we can't randomly assign the treatment, we may use the instrumental variable, or ID, where we use a randomized variable that influences treatment but does not directly affect the outcome Y. This allows us to estimate the average treatment effect given compliance, called the local average treatment effect, or LATE. Well, what if we can neither randomize the treatment nor find an instrument variable? In that case, we can try controlling confounder X and estimate the treatment effect conditioned on confounders called K, conditional average treatment effect. So even when RCT, randomized control trial is possible, sometimes we may be interested in estimating K over 8 average treatment effect when treatment effects are heterogeneous across the population. In other words, if some users respond to the treatment better than others, average treatment effect for the whole population might be 0, while K for those users can be positive. And identifying those users can help design an efficient targeting strategy. And ML algorithm plays a vital role in CADE estimation because it can learn the complex functions between high-dimensional confounders versus the treatment and outcome. Let's see how different causal ML methods use machine learning algorithms in CADE estimations. There are roughly 4 kinds of causal ML models. First, meta-learning. Second, double or doubly robust learning. Third, tree-based models. And fourth, neural network-based models. First, meta-learning is the simplest causal ML. It trains ML models that predicts outcomes with and without treatment, and then combines them to calculate CADE. S-learner, or single model learner, fits one outcome prediction model with a treatment variable. Then it predicts the outcome with and without treatment by setting the treatment variable to 1 or 0, then obtain CADE from the difference between them. T-learner, or tool model learner fits 2 outcome models, not one for control and the other for treatment. Then it gets outcome predictions with treatment from the treatment model and outcome predictions without treatment from the control model, then obtains K from the difference between them. X-learner or cross-learner fits 2 outcome models like T-learners, then use them to get counterfactual outcome predictions and the treatment effects from the difference between the actual and predicted counterfactual outcomes. It then fits 2 treatment effect models, one for control and the other for treatment. It obtains K from the weighted average between 2 treatment effect predictions from them. Next, double learning and doubly robust or DR learning train a model that predicts outcome like meta-learning, as well as a model that predicts a propensity score, which is the probability of treatment given compound X. It then combines outcome and propensity score predictions to calculate K. Double ML or R-learner use the residual on residual regression with cross-fitting. It first fits the outcome and propensity score model separately with cross-fitting. Then it computes the residuals on the outcome and propensity score estimate, and it fits the treatment effect model to predict the outcome residual from the propensity score residual. On the other hand, DR learners use the doubly robust regression with cross-fitting. It separately fits the outcomes with and without treatment, as well as the propensity score model. Then it fits a treatment effect model using the doubly robust regression. Double and DR learning can use arbitrary ML algorithm at each step, like meta-learning. Unlike meta-learning or double or DR learning, tree-based models and neural network-based models require some modification in standard ML algorithms. For example, tree-based models modify the node split criteria of regular standard CART or random forest algorithms. Causal tree is an extension of standard decision tree algorithm. It splits the nodes to maximize the variance of treatment effects across leaves while minimizing the weighted within leaf variance. And causal forest is a bagging ensemble of causal trees. It trains multiple causal trees and combines them together. GRF, generalized random forest, is a generalization of causal forest. It uses residual instead of the outcome and propensity score, very similar to double ML. Lastly, neural network-based models train outcomes for control and treatment, as well as the propensity score simultaneously. For example, TARNet and CFRNet train 2 heads to predict the control and treatment outcomes, and these 2 heads share the same representation layer. On the other hand, DragonNet trains 3 heads to predict the control and treatment outcomes, as well as the propensity score simultaneously. So let me summarize. In summary, meta-learning combines outcome models with and without treatment. There are S, T, and X learners. And double and DR learning combines the propensity score and outcome models. Popular models in this category include the double ML, R learner, and DR learner. And meta-learning and double and DR learning use standard ML models at each step and combine their predictions to estimate K. On the other hand, tree-based algorithms require modification of a node split criteria of standard CART or RF. Examples are causal tree, causal forest, and GRF. Lastly, neural net-based models such as TARNet, CFNet, DragonNet train outcomes for control and treatment and the propensity score simultaneously with a shared representation layer. Okay, that was a mouthful. It's great to have so many causal ML algorithms available, but at the same time, it might be a bit overwhelming to get started. How can you get started using causal ML methods then? Here comes open source tools for the rescue. So there are a growing number of open source causal ML tools. The author of GRF implemented the GRF library in R, and Python has DUI and CausalNext packages for causal identification, and EconML causal ML packages for causal estimation, more specifically Kate estimation. So first, the causal ML package provides scikit-learn-like APIs for many ML-based Kate estimation methods, including uplift tree, causal tree, ST, XLearners, RLearners, DRLearners, DragonNet, and CVA, causal effective variational autoencoder. It also provides utility functions for simulation, visualization, sensitivity analysis, evaluation, and various example notebooks. Similarly, EconML provides many ML-based Kate estimation methods and excellent documentations. And EconML and Causal ML development teams hosted a joint tutorial and the Causal ML in Practice workshop at the KDD conferences. We plan to continue the workshop next year, so if you're interested, please join us next year at KDD in Barcelona. Next, we will review a couple of industrial use cases of Causal ML in practice. These use cases were originally shared at the EconML Causal ML joint tutorial at KDD 2021, and the slides and example codes are available from the tutorial website linked here. First use case is the observational causal inference for cross-selling. Our goal was to understand the effect of existing Uber ride users becoming Uber Eats users on their customer lifetime value. The challenge here was we couldn't do an A/B or randomized test because blocking random Uber ride users from using Uber Eats would harm the company business as well as user experience. Also, there was substantial heterogeneity between the control group, who are Uber Rides users without Uber Eats orders, and the treatment group, who are Uber Ride users with existing Uber Eats orders. So we started with the traditional stratified propensity score matching to find the comparable control group. Then we trained the meta-learning algorithms to control confounding further. Then we tested and evaluated the robustness of treatment effect estimation using sensitivity analysis. The next use case is targeting optimization for online advertising. Here, we aimed to select only persuadable users likely to convert only given ad exposures. The challenge was we needed to separate persuadable from the always taker who would convert regardless of ad exposures. For that, we first launched an online Explorer data collection experiment where we randomized the ad exposure across users to get the training data for our models. Then we trained meta learners and evaluated their incremental gains. After we picked the targeting criteria based on the model evaluation, we launched an exploit experiment with a random explore holdout. So for exploit group, we targeted users based on the predictions from our meta learners, while for the holdout group, we still randomized ad exposures. Here is the illustrative result showing that by targeting 60% of users, we could get 80% of total possible gains, which result in a 47% increase in return on ad spend or ROAS. And that brings us to the end. Thank you for your attention. Let's go to Q&A.
Thanks a lot, Jung. I'm impressed, really on timing, precisely 15 minutes. Thanks a lot for your presentation. And we have a couple of questions. Oh, we have more questions. So first, we, for example, have a question from Gabriel asking, you show several methods, obviously. What method do you think is the best for estimating individual treatment effect?
Mm-hmm. Well, I'd say it always depends on the data and the goal and situation. So for example, in the cross-selling use case I shared, we use the observational data, not randomized test data. Then the focus would be getting the correct estimate instead of identifying high K users for targeting. In that case, we may use a simpler but more explainable model with good theoretical properties, such as double ML model with a simple linear treatment effect model at the last step. Double ML provides a good convergence guarantee and with a good theoretical properties. And then if we use a simple model or explainable model at the last stage, then it helps us interpret the result better and get more confidence on our causal estimate. So if the correct measurement is your interest, then I would go with something like a double ML. But if your goal is to identify high K users to maximize the targeting performance, then I would recommend that you try out multiple K estimators and compare the performance, compare the gain using either area under uplifted curve or Queenie score, something else, and then pick the one that gives you the highest lift to highest incremental gain compared to others.
Mm-hmm. And I think also a really question that everyone has on their mind. So given that in most, like you don't have ground truth, how do you validate the causal ML methods?
Yeah, that's really challenging, and we can try.
That's why we're asking you, on that.
Yeah, I think Totte also mentioned it. We can use combinations of different approaches. So, for example, to evaluate the goodness of or correctness of an algorithm in general, then we can always use simulation where we do have access to the ground truth and we do have access to true data generation process, and we can check which assumption, which condition model perform better or worse. Also, we can use uplift or Queenie curve to identify the gain and compare gains across estimators. And we can use a sensitivity analysis to test how robust those causal estimates are in different situations. And we can use a feature importance and explainability to see whether the estimate agrees with domain expertise, which can be valuable information. Again, nothing is perfect, but each provides some information, and it may help us make better decisions.
Okay, and last question. So we have next paper, but last question. So Jonas is asking, is there a way to integrate assumptions on the data generating process, example given, through a causal DAG into causal ML models?
Mm-hmm. Yeah, I think so far the development in the causal identification field and causal development in causal estimation field has been somewhat separated, but I see some research in recent work coming out at the intersection of two. One example was recent work from Elias Barenboim's group, Judea Pearl, who trained under Judea Pearl, and they proposed a neural net-based algorithm that combines both identification and estimation. We don't have a good portfolio of such method available yet, but I think that's the direction many people are pursuing. So we may see good result in methodology available soon.
Okay, brilliant. Thanks a lot for your presentation again and for all your questions.
Good morning, good afternoon, everybody. I'm Robert Ness. I'm a researcher at Microsoft Research, and I'm going to talk today on LLMs and causality. This is a technical talk, but the great thing about technical talks when it comes to large language models is I can show you prompts and generated text and call that technical. So, but then towards the end of the slides, we will see some actual code. So let's jump right in. First off, if you're interested in this topic of large language models, I run a cohort course, this one starting this week on building apps of large language models. I encourage you to check that out if you're interested. I also have a book here on causal AI. Some of the tutorials that I'm going to show here, which I'll provide links to, are coming from a chapter in this book. So I encourage you to check that out if you want to go deeper. And also part of what I'll talk about today are some of the empirically validated results from a paper from my colleagues and I at Microsoft Research, Amrit Kissim and Amit Sharma, as well as a colleague at University of Chicago, Chun-Hao Tan. So the first thing I want to do is talk about the ways that we can use large language models to augment a causal analysis. So I think you'll see some parallels with somewhat of what Totte just talked about here. The first one being the major use case of building a causal DAG. So as was just mentioned, we need to use a causal DAG or some other way of representing our causal assumptions about the data generating process. And for a lot of people, specifying a causal DAG is quite daunting, right? You need expert knowledge. And in an era where there's a lot of emphasis on kind of radical empiricism, the idea of taking domain assumptions and making them explicit in your model is intimidating. And what if you're wrong? What about if you've misspecified your model? So model LLMs can act as a very valuable approach to leveraging public expert knowledge to build the DAG. So in Todd's talk, he just talked about this domain expert who would come in and kind of drop some domain knowledge and then leave. Well, now you can use large language model as a kind of knowledge base of collected information from various domain experts, right? So to give an example, and again, there's caveats always, but let's just give an example to give you an idea of what this looks like. Say you're a helpful causal analysis assistant. So this is me making a prompt. So starting off a system prompt, kind of telling the large language model what the role it should play. I'm interested in modeling the relationship between smoking and lung cancer, providing me a causal DAG that captures this causal relationship. And certainly the first thing it does is it kind of gives me a sketch of what I'm looking for. It tells me what potential confounders were. So smoking and lung cancer, confounders could be genetics, age, environmental exposure, other health factors. And then it gives me a sketch of the DAG. Jumping ahead a little bit, it also gives you some potential mediators, right? So that one could hypothesize that smoking could cause lung damage, which in turn causes lung cancer. And so in this case, a mediator, something that's on the direct path between the treatment and the outcome, it's suggesting that as part of its result. Now, this is a very well-known kind of causal DAG, and results might vary depending on your domain, but it's a very useful tool to bootstrapping that causal DAG building process. And I can go further. So now I'm going to say, hey, give me some instrumental variables, right? I'm going to ask you to be brief because large language models can be particularly verbose. These are all actual generations from ChatGPT using the GPT-4 version of the model. So the most cutting edge model available at presently. So it gives me two good instruments, cigarette tax or price. Again, an instrument is something that causes the cause of interest and causes the effect indirectly through the cause. And these are useful in causal effect estimation. So cigarette tax and price, as well as anti-smoking campaigns or legislation. And then it goes on to tell me what I would expect from a good or a valid instrument. Going ahead, it's also useful for generating code for DAGs or other elements of my causal analysis, right? So cutting edge large language models are aside from being trained on large corpuses of natural language text, it's also trained on code, on, say, for example, much of the code that's available on the internet, such as sites like GitHub. And so this will include libraries for causal analysis, and the more popular the library, the more widely, the more that library is represented on the internet, the better. And so this will greatly speed up my causal analysis by helping me as a data scientist handle some of the boilerplate of my causal analysis, right? So in this case, I'm going to ask ChatGPT to give me the DAG for it'll give me code that implements the DAG that it just suggested here. And so I'm asking for it using the do-while library. And as you can see here, it generates some code here, and it gives me do-wise approach to specifying the model, which is to say, I specify the various I specify the nodes in the DAG according to what role they play in the causal inference, in this case, causal effect estimation. So it's going to give me a treatment. Specifies my treatment as smoking, my outcome as lung cancer, my confounders as common causes here, and instruments here, for example, as price. And then it goes on to give me the full actual analysis workflow in do-why, which is to identify the estimand, and then to estimate the causal effect using, in this case, instrumental variable based estimator. And it also gives me, so my code runs in the first pass, some synthetic data here that looks like the data that I would need for this analysis to work. And then I could go in and edit this code such that it's now using, say, data from my actual domain or my actual problem, real data. Now, going beyond the DAG, the large language model is actually quite good at giving us explanations of mechanisms. So Dr. Pearl mentioned the causal hierarchy, and the third level hierarchy is assumptions about how causes affect the effects. You can't look at a DAG and see that, right? Because a DAG just shows us what causes what. It captures our level 2 assumptions in the causal hierarchy. We have some formal models for capturing level 3 assumptions, or assumptions about how, structural causal models, and that's a mathematical formalization. And the problem with that is that we often don't have a knowledge of the mechanism at a level of mathematical detail. Maybe in spaces like natural sciences, like physics or biochemistry. Maybe in biochemistry we can use like Michaelis-Menten kinetics or something like that. But when it comes to, say, ad spend on brand engagement for brand awareness, for example, I'll show that example in a second. There's no math that maybe comes readily to our minds for how to connect those two things. But what the large language model can do is, again, leveraging common and expert knowledge, give us natural language explanations of these mechanisms that go beyond the DAG, but not quite to the level of mathematical specificity. So, for example, here, I say, you are a helpful causal explanation generator. Provide a characterization of the causal relationship between ad spending and brand awareness. Be concise enough to fit a single slide in a slide deck, because I was trying to get it to fit in this slide deck. And it actually just generated the entire slide for me. So this is actual a GPT-4 generated slide. It talks about monotonicity in the sense that as ad spending increases, brand awareness generally rises and does not diminish. And talks a little bit about the mechanism here. That's more ad spending means more frequent and widespread exposure of the brand to the audience. Diminishing returns, right? So something that we might capture in like a sigmoid curve, that's with additional spending, we're going to get the diminishing returns in terms of the amount of increased brand awareness due to reasons like ad fatigue and market saturation. And finally, it talks a little bit about other things that are going to be driving brand awareness. So making it clear to us that this isn't solely focused, that the relationship isn't, the brand awareness doesn't solely depend on ad spending. An additional thing which we've seen some really interesting case studies and research and have validated on some cognitive science-based benchmarks is something I call establishing a causal frame. So what does that mean? So the causal frame problem, maybe if you have a background in AI, you've heard about the frame problem. The idea basically is, how do we decide which variables are relevant to a causal problem? Now, if you're a causal inference expert, you might be thinking about things like causal sufficiency, but for something like an AI system, this is, rather than a technical or mathematical concept like sufficiency, is focused here on essentially what it's seeing inside the training data, what experts are saying is relevant to a problem. So to put it another way, using philosopher and AI researcher Claude Glymore's quote, given an enormous amount of stuff and some tasks to be done using some of the stuff, what is the relevant stuff for the task? And LLMs are very good at distinguishing what is the relevant stuff from what is not. And so, for example, you are a helpful causal reasoning assistant. This is my prompt. Consider the following story. Jake is logged into an office network. There's an open shared folder on the server. Jake is transferring files across the network and accidentally clicks on the folder, starting a process that consumes a significant amount of bandwidth. This causes the network to slow down. How responsible is Jake for the network slowdown? So it gives me talks about, it analyzes the problem for me, talks about that, Jake was a direct cause, and talks about responsibility and intention. If you're making causal judgments about an individual's responsibility, often intention is very important. But now it jumps into the frame. So this is what's really pops out to me is interesting in terms of this ability is, for example, talks about the prevention mechanisms. Like, was there anything, a warning or some kind of barriers that would stop Jake from clicking on this file? I didn't say anything about prevention mechanisms in the prompt or in any specification of the problem, nor did I talk about any knowledge or training that Jake should have had to know whether or not to click on a certain file or whether or not the system was designed a certain way. And taking a step back, if we think about, given an effect, and we think about what causes it, and then what caused that cause, and what other causes those causes, we can go all the way back to the Big Bang, right? So how does the system know what to include as a relevant cause? So why not say that Jake, was Jake on a Unix or a Microsoft system, or a Linux or a Microsoft system, or why not ask if it was a holiday and that's maybe there was extra or traffic because of the holiday, or less traffic because of the holiday. It chooses things to include and things not to include, and those things tend to align with what humans tend to think is relevant to a problem, which is so kind of benchmarking against as a data scientist who's trying to frame the problem or build a system around the problem, the ability to kind of emulate human judgments about what goes in and what goes out of the model is an important feature. Understanding and contextualizing causal concepts. So it can be challenging to understand some of the formal concepts of causal inference, apply them to real world problems. So this morning, Dr. Pearl gave an example of necessary causation, or specifically probability of necessary and sufficient cause. And he gave an example from from medicine or from policy related to public health policy related to treating people for an illness. And if you're now working inside, say, Netflix, and you're trying to understand whether or not to change your algorithm with respect to some set of individuals, it can be difficult to figure out how to apply this concept to that particular problem. Now, large language models are good for that type of contextualization and understanding. So I'm going to ask it, firstly, if it can explain necessary causation for me. It does. In other words, so it says that necessary causation, something is a cause is a necessary condition for the effect to occur. In other words, if it didn't happen, the effect wouldn't have happened. Great. Maybe I have a background in legal theory, or I'm an attorney, and I'm thinking, wait, that sounds like something I've heard before. Can you contextualize it in the realm of legal theory? It says in legal theory, necessary causation, often termed but-for causation, is a foundational concept used to establish a direct link between a defendant's actions and the harm suffered by a plaintiff. Great. Now, as a Netflix data scientist, I'm like, okay, let me apply it to this problem. Give me an example of necessary causation that involves a Netflix user unsubscribing from Netflix. A necessary cause for a Netflix user unsubscribing from Netflix might be the exclusive content that is only available on the platform if a particular show or movie that a user is deeply interested in is removed from Netflix while remaining available somewhere else. Then the removal of that content becomes a necessary cause for that user's decision to unsubscribe, which is very valuable if you're trying to take some of these advanced ideas and apply them to your specific problem space. Similarly, we want to be able to formalize our causal queries, right? So using that exact same example, I might need to now, if I have some software, I want to say apply some of the identification bounds or partial identification bounds that Dr. Pearl was talking about this morning. I need to take my problem that I'm able to articulate in natural language and convert it into some mathematical expression that I can then apply some mathematical analysis to, or some algorithmic analysis to, assuming that I can take that expression and represent it in code or in some domain-specific language for my causal query. And so here, so you're in this, for example, you're a helpful causal inference assistant. I'm considering a counterfactual inference problem I have in the context of Netflix. I have the following query. There is a set of users who unsubscribed after content was removed from the platform. What is the probability a given member of the set of users would not have unsubscribed had the content not been removed? I mean, think back to Dr. Pearl's example this morning. You have a set of people who, for example, have not, who took a treatment and then, well, who didn't take a treatment, well, let's see, who took a treatment and then were healed. What's the probability that they would not have healed had they not taken the treatment, for example? Like, that's making that jump from that public health domain to this particular domain could be challenging, and taking that natural language from this Netflix domain and turning it back into the same counterfactual notation that Dr. Pearl was using this morning could also be challenging, and the large language model can help us. So certainly Pearl's counterfactual notation offers a concise way to express some queries. It tells us, okay, X here is going to be whether or not the content was removed, Y is whether or not the user unsubscribes, and we can rewrite it as this expression here, where Y sub X equals 0 is the counterfactual outcome. Y had X not been set to 0, i.e. the content is not removed. So that's very useful, but we have to we have to be cautious. Again, the LLM can take us from conceptualization to formalization, but the LLMs can also hallucinate. So what does hallucinate mean? Let's give an example. I'm going to ask the LLM now to give me some more code now. So give me some code that takes that expression that of probability of necessity, in that Netflix example, that's removing the content was necessary for the user to unsubscribe, and give me code that allows me to implement, to estimate this quantity. And it does it. It gives me a expression here. So treatments being removal of the content, outcome being whether or not they subscribed, and it gives me this formula for estimating the probability of necessity. And this is very useful, very interesting. The problem, of course, is that this particular answer is incorrect. It gives me the wrong answer. And what's particularly insidious about this is that it's close to being right. In fact, this particular answer, and of course, if you regenerate, you might get something different, is right, but only under certain strong assumptions. And those assumptions, I did not provide those assumptions in the prompt, and they were not explicitly stated in the generated text as a caveat, like, here's how you can estimate probability of necessity, but you got to make sure that these conditions are satisfied. It didn't say that. It just gave me this formula, and and gave me the impression, if I were a naive user, that I could just apply this in any setting, and that's not true. And so it's important to remember that these LLMs are trained exactly to do this, to provide very convincing answers. Their objective function during training is to predict the next token in a sequence of text. And then they're just subjected to maybe instruction-based fine-tuning to make it better at following instructions, and then reinforcement learning with human feedback, which literally trains it to be as human-like as possible. In other words, training it to be as convincing as possible, even when it's wrong. And so what does that mean? Practically speaking, it means that I could catch that hallucination because I understand enough about necessary causation to know that something was afoot. And so similarly, that if you're going to use this to augment your causal analysis, you have to know enough about what you're doing in order to be able to detect when the LLM might be going off the rails. And so that means it's not quite at the level of completely automating away causal analysis, such that a person does not have to know anything about how causal inference works in order to use this. But given that you know enough about a kind of causal inference task, enough to know when things start looking hinky, it's a very useful tool for kind of putting that causal analysis on rails so that you can get to more results, better results faster. Now, happy to take questions on that. I'm going to switch it around a little bit, the remainder of my talk, and talk about, so this was using how we can use LLMs to augment a causal analysis. I'm going to talk about how we can use causality to augment a large language model. And this is kind of new work that we're working on at Microsoft Research. And let me give you a flavor for what that might look like. So there is structure often in our training data, in our text, in our images, whatever it is we're using to train generative AI. And this structure, but when we train them, we often train them on flat forms of the content and ignore this structure. To give an example, right? So if maybe the large language models like GPT-4 train on lots of newspaper articles available on the internet, and it's just the article, just the final article, some pages from a code repository on GitHub, maybe some images in multimodal models or image models like Midjourney or Stable Diffusion. But again, there's lots of structure here. So for example, this newspaper article, if a New York Times journalist maybe has been working on this story for a while, they have lots of notes, they have lots of edits, they have drafts, they have feedback from editors. All of those are connected in some kind of history for this newspaper article. And similarly, perhaps even more structured is the commit history of a code repo, right? So you can see not just the code, but how it evolved over time. Perhaps you can even compile the code into executables and see the relationship, have something that maps the raw source code to the low-level code in the executables. Similarly with illustration, if we're using some kind of computer animated design software, if we opened it up, we would see the raw files, we would see, say, for example, layers in the illustration and the metadata associated with each of those layers, maybe even some also drafts for how those layers developed over time. It's very hard to use that kind of deep structure when you have very, very large models that require very large training corpuses to train the very large sets of parameters that parameterize these models. But the research, one kind of interesting direction in the research is getting to better LLM performance with less data and less parameters. I'll make a call out to some recent work by some of my colleagues at Microsoft Research. Textbooks are all you need, which trains a performance model on 1 billion tokens by using very high quality, 1.3 billion parameters using some very high quality data sets and what that allows us to do is start to explore as that research develops, we start to see the opportunities of leveraging this unused structure, going more into depth than breadth during our training procedure. And sometimes that structure is causal. So to give an example, really just kind of to make this concrete in your head, I want you to imagine that you're working at a production company that produces scripts. This is very germane to some of the writing strikes that we're having in the entertainment industry in the United States right now. And you can imagine that all the writers are using some kind of writing software that is following a kind of 3-act archetype template, right? So that's 3-act like boy meets girl, boy loses girl, boy gets girl back, that type of template. And from a causal standpoint, we can think of it as the events in Act 1 causing the events of Act 2, the events of Act 2 and 3 causing the events of Act 1 and 2 causing the events of Act 3. So to kind of see what this would look like, I want you to imagine now that we have a bunch of, say, scripts, a big corpus of scripts, talking about a specific archetype where there's a king and doing something in Act 1, a prince doing something in Act 2, and the results for the kingdom in Act 3, right? And just to keep things kind of limited, we'll say that's essentially what's happening is that in Act 1, the king is declaring war or negotiating peace, or he's falling ill. the prince is leading an army, abdicating a throne, or marrying a foreigner in Act 2. And the kingdom either wins the battle, falls into poverty, or experiences prosperity in Act 3. Now, one thing to mention here is that, there's going to be some biases in these data set that maybe that's usually that prince leading the army tends to go with king declaring war, that negotiating peace tends to go with marrying a foreigner. And so if we kind of bunch these all up into one script, it's going to learn all of those statistical patterns. So if we want to kind of go beyond that, those patterns to generate new data sets, new stories that follow the same archetype that we haven't seen before, it's going to be quite difficult. So some examples. So you can see these, you can download this data rather than full kind of acts. I'm just having short vignettes here, right? So here's one for negotiating a treaty, negotiating a peace. So king brokers a peace treaty with a rival kingdom. And the second one, a wise king successfully negotiates a peace. Third one, also negotiating a peace. So these are all three about negotiating a peace, but the text is allowed to vary because we're working with natural language. Similarly, for the prince, this one is marrying a foreigner. The second one is also marrying a foreigner. The third one is leading the army. And then for the kingdom, again, so falling into poverty in this first example. Second one is going to victory. The kingdom experiencing victory in the second example, and then in the third example, another one about falling into poverty. So two about poverty, one about victory, but they're all worded differently. So we want to be able to build a model that works directly on this natural language. And so again, we can just, based on our structural understanding of the problem, we can specify a DAG. And now what we have to do is train model that's going to learn these conditional distributions factored along the DAG. So the probability distribution of the king actions, the probability distribution of the prince actions given the king action, the probability distribution of the kingdom outcomes given the king and the prince actions. And so what I'm going to do in this tutorial is I use GPT-2 using Hugging Face Transformers library to train a generative model on the king's actions. So I just download GPT-2 essentially and fine tune it on these vignettes. The full fine-tuned version is available on Hugging Face Hub, so you can just download it directly. Similarly, given the king's actions, I want to model the prince's actions, and so I'm going to use a BART sequence-to-sequence transformer to do that. And I'll also use a sequence-to-sequence transformer to go from the king and the prince's actions to get to the kingdom's outcome. And now to implement this in code, I want to build something that looks like a probabilistic graphical model. And to do that, I'm going to use Pyro. Pyro is a tool for building probabilistic models on top of Torch. I'm going to use a mixin that builds Torch distributions, and I'm going to do it using my pre-trained model. So that's specifically to do this in Pyro, I need just to pass in my model, my language model. I need to be able to generate some text under the sample method, which happens here, and then I need to be able to get the log probability of some generated text under the distribution, and I'm going to use that using this compute log probs, which will take the logits that are provided by by Hugging Face transformers and computing the log probability of the entire sequence of text. And then from that, I can build a causal graphical model here, where again, here you can kind of see the implicit DAG here, where I sample the king text. Given the king text, I sample the prince text, and then given the prince text and the king text, I sample the kingdom. This is working on the level of embeddings, but then I can just decode them back into text and then pass out a fully generated script, if you will. Now, because it has this causal structure, I can apply the tools of causal reasoning. So for example, I can use a do operator to apply an intervention that sets this print story to a specific story here using this. So I take the model, apply the do operator that fixes prints to a certain print story. And then if you go through the tutorials, what you'll see is that I'm going to compare this to this interventional distribution of kingdom given a specific print story to just the conditional distribution of the kingdom given the print story. Now, our knowledge of causal inference tells us that these two things should be different. And indeed they are. So the way I show this is by sampling stories from each of these distributions, the interventional and the conditional distribution, and then selecting top terms by TF-IDF and plotting them. And we can see kind of a very distinct distribution in terms across the two distributions. And the reason is because, for this particular story, maybe a very narrow set of king actions are correlated with the story, and then those get overrepresented in the evidential model. Well, but when I apply the intervention, the causal relationship between the king's behavior and the prince's behavior is broken by the intervention, and the king's behavior is allowed to vary, giving me an out of distribution, an out of training data, training distribution story that I can use to generate new stories, and then and use that to apply other kinds of intervention-based causal queries on my natural language model data set. So what I'm doing here is, rather than asking these questions, can large language models reason causally, I'm saying, can we build a large language model that can reason causally? And the answer is yes. If you can take the causal structure of your problem and make sure that you explicitly represent it in the structure of your model, your large language model. So I'll stop there if there's any questions.
So thanks a lot. So I'm having a note for myself. I need to rewatch. It's like a lot of stuff. And I have quite a few questions. So thanks a lot for the presentation. Where do I start? So let's start. Everyone is worried about hallucinations, obviously. And it's like the biggest question. We know it's hallucinates. So can you actually rely on this? So you said like we need to be cautious about it, but how would you change the process or attitude to this kind of approach to make it feasible to use LLMs, but at the same time to check for these problems? Do we do something statistically on top of it?
I mean, so I think there's some interesting practical questions here, and then there's some research questions here as well. So from a practical side, let's say with the base use case of generating a causal DAG, if I go into the model and I ask it to give me a causal DAG, well, I can then do some basic validation steps with that DAG. I can say, for example, as the causal Markov assumption Dr. Pearl mentioned it this morning is that these separations in the DAG, implied conditional independence statements in the DAG, should correspond to evidence of conditional dependence in the data, or and maybe if not conditional independence, there's some other causal constraints that we can that are implied by the DAG that we can now test for in the data, right? So if for example the LLM gives you a DAG and that DAG says two things should be conditionally independent, great, run a conditional independence test and see if it holds up. So right, so it's still a DAG, and we should still go through the process of validating the DAG, and of course we can even ask the LLM to help us generate the code that helps us do the validation. And so that's one. From a theoretical standpoint, I think it's quite interesting. One of the things that's helped me in terms of understanding the hallucination problem is we've been talking about the ladder of causation or the causal hierarchy, and part of that, a formal result from the causal hierarchy is the causal hierarchy theorem, which says that for a given causal query, if it's a level 2 query like an intervention or a causal effect, or a level 3 query like a counterfactual, the assumptions required to identify that query have to come from the same level or above, right? And so if, for example, that means that if, for example, I ask a causal question of the large language model and I expect it to get it right, and let's assume that it does get it right, what has to happen is either I've specified enough information in the prompt itself, or that's causal information that's required to identify that query was in the training data, which we can never verify, particularly with proprietary models, or is somehow encoded as an inductive bias in the architecture itself, again, which would be very difficult to verify. So that doesn't solve the problem, but it helps us parse the problem a little bit. In causal inference, we know that there are things you can't identify even with infinite data. And so that's very important for when we're thinking about, building the next large language model with trillions of parameters, and that's not an exaggeration. And so I think that causal inference theory has a lot to tell us about what are the sources of hallucination, how we can treat it, and what won't work. Say, for example, more data. Like if you don't have enough information in your prompts, you cannot expect it to just magically learn it from the training data, unless particularly if you don't have access to it.
Thanks a lot. I feel like I'm on the radio, so I have greetings from you, from Jeremy. Jeremy has a really difficult surname. It's Jeremy, I will spare reading it. But Jeremy was your reviewer for the first draft of your mining book, so he's really glad to see you speaking today. So it's like right away, I'm passing you greetings. So yeah, I think I have seen a couple of questions which are actually covering what you just said, that LMs are trained specifically on some data. How can we maybe think about applying them to our data? We hope that data, which is proprietary to BP, to, I don't know, Microsoft, is not part of LMs. Can we then think about some way of using what you've just shown, but on our proprietary data?
So Microsoft, Amazon, Google, a major service that is being developed for commercial users is the ability to kind of host instances of these large language models that are walled off from the outside. So, for example, you'd be with Microsoft, you'd be able to use GPT-4, but OpenAI wouldn't see your queries. So that's definitely I think that's what you meant, right? Like from a privacy or a proprietary safety standpoint, the ability to use things that are essentially secrets and not have that be exposed. Was that what you meant?
I think it's like we hope that proprietary data is not part of OpenAI LLM. I don't know, as a person who knows, do you think passing it as a context of your query, or just like using RAG pattern, something like this can help us to kind of have that data part of the LLM brain?
Yeah, so you mentioned RAG, for example, so that's retrieval augmented generation. So that's in fact, that works very well with the use case of, say, building a causal DAG from, say, your proprietary knowledge base. So if, for example, you had a large amount of information in text form about the structure of your problem domains, and you could then say specify causal query inside the prompt, it would use something like a nearest neighbors algorithm to find documents from your knowledge base that were relevant to that prompt, and then perhaps try to assemble a DAG based on those documents. That's definitely something that would work today, and I think we would expect to get better in the future.
Brilliant. Thanks a lot.
Hi, everyone. Thank you very much for the invitation to speak. It's great to be part of spreading the excitement about causal inference. So a brief bit about me. After 15 years in a permanent academic faculty position, I left to become a freelance data scientist. And I've spent the majority of my time working as part of PyMC Labs, where we help companies turn data into insights in order to drive business decisions. Now, before we kick off with the slides, I would just say I became a father just 2 weeks ago, so I promised to do my very best to convey why you should be excited about Bayesian causal inference despite my extreme level of sleep deprivation. So let's dive in. In this talk, I'm going to focus on this map of uncertainty and causality. So on the y-axis, we're climbing the ladder of causality with statistical associations at the bottom and causal reasoning at the top. On the x-axis, we have the degree of uncertainty quantification with traditional frequentist or point estimate type of approaches on the left and Bayesian methods on the right. So I'm going to be a little bit bold and just place much of data science in the bottom left of this plot. So there are well-known and widely used methods and software packages that we can use to do a whole bunch of things, including predicting outcomes, forecasting into the future, and generating insights from your data. And we can live down in this corner and be perfectly happy for a while. However, taking a purely statistical approach really restricts us in the kinds of questions that we can answer. So fortunately, Judea Pearl, amongst others, have written extensively making the case for climbing the causal ladder. So I don't necessarily need to repeat all of these arguments here. But in short, if you interpret purely statistical inferences in a causal manner, that can lead to entirely unexpected effects once you or somebody else starts to intervene in the system by acting in the world, for example. Secondly, causal approaches are definitely required in order to answer these rung 2 and 3 interventional and counterfactual questions. So we have heard about some of these today. Examples of interventional questions would be things such as, how much should I spend on advertising in order to maximize new customer signups? Or what level of discount should I give in order to maximize profit? Counterfactual questions would be of the flavor like, what would have happened if I'd spent my marketing budget differently? Or what would the UK's GDP be now had we not voted for Brexit? So we are already seeing people, companies, and scientific disciplines venture upwards up the causal ladder to address questions which require causal approaches. The slight kind of drawback or the difficulty of this is that it does require a lot of upskilling. Let's say if you've got a traditional data science or statistics type of background, there are loads of new causal concepts to learn. But the good thing is that there are a whole bunch of different software packages out there. And we're also starting to see the emergence of books on causal inference focused towards practitioners, which are more kind of software heavy rather than maths and theory heavy. Now, I think that what will happen, my prediction, is that many people will stay on the left-hand side of this space, sticking with traditional frequentist or machine learning type methods. And that is absolutely fine. However, we are seeing a meaningful migration eastward. So many are finding that Bayesian methods are very well suited to their problems. Many are finding that Bayesian methods offer advantages over traditional approaches. So let me just give a very brief primer about what Bayesian inference is, if you're not already familiar. So one way of explaining it is that it is essentially the optimal way to revise your beliefs about the world in the light of new evidence. So that's a really important and useful thing. It also avoids some interpretability problems and some of the strict assumptions that are associated with frequentist statistical methods, for example. And it also allows you to quantify your level of uncertainty. And this is really crucial when we're making high stakes decisions. very importantly as well, it allows you to leverage your valuable personal or institutional domain knowledge into models via either the DAGs that describe the causal story of your data, or the Bayesian priors themselves. And finally, in the kind of Bayesian sphere, it is more standard practice to build bespoke models that fit your exact problem, rather than trying to shoehorn your problem in to fit into a prepackaged statistical solution, for example. However, my contention for today is that combining the two and taking a Bayesian causal inference approach is particularly compelling. So, in short, the payoff is that we can answer the kinds of questions that we really care about, and they're the ones that we need to be at the top of the ladder for. And we get all of the benefits of the Bayesian approach that I just outlined. But I would say, in addition to that, I think there's extra synergy. So, for example, both Bayesian and causal approaches embrace subjectivity. Some people are very tempted, understandably so, to remain fully objective, and they want to just let the data speak for itself. But both Bayesian and causal approaches kind of take a slightly different stance and say that really you as a practitioner need to bring your subjective knowledge about how the world works, the data generating process, to the table. And Bayesian approaches also kind of say that we can do better in terms of inferences by incorporating prior knowledge, which is inherently subjective, quantitative, but subjective in nature. So if you buy that argument and you're interested in the top right-hand area of our chart, the question is, what tools can we get there? Now, this is not a systematic, wide-ranging survey. I'm going to be quite selective, focusing on PyMC. Now, PyMC is a Python-based, I'd say very mature at this point, open source probabilistic programming language, and it has a very large and diverse user base. Traditionally, it has been seen as a purely Bayesian statistical inference library, but we are finding that we only need to make some minor modifications to enable it to address Bayesian causal inference questions. We are also finding that climbing up the causal ladder is perhaps a little bit easier if you already have a bit of Bayesian background, because you already would have acquired a bunch of concepts, not by no means all of them, but many of the concepts that you need for causal thinking. So we, as in the open source PyMC and more broadly probabilistic programming language community, are really starting to embrace causal concepts to help make Bayesian causal inference more accessible to everyone. We're also building open source packages. So Causal Pi is one that I released a little while ago, which is built on top of PyMC, which lowers the barriers even further to give quick, easy access to a subset of causal inference problems revolving around quasi-experiments. So it has features that help you do things like synthetic control, difference in differences, regression discontinuity, and these kind of things which you'd broadly label as econometrics, perhaps. Now, there are, of course, other libraries, but I'm focusing on where my expertise lies. So in the rest of the talk, let me just give you a brief run through of how we might use Bayesian causal inference to address a very simplified problem. So I'm going to talk about this very generically. So let's think about a particular treatment. So a person can either receive treatment or they can not receive the treatment. And what we really want to understand is what is the causal effect of receiving the treatment. So this, if you want to think of something concrete, it could be things like, does running an ad campaign increase customer signups? Or you could ask, does drinking coffee increase productivity? Does offering customer discounts decrease customer churn, for example? So one of the ways that we could approach this from more of a statistical background is simply to plot the distribution of outcomes that we see for those people who did not receive the treatment and for those people who did receive the treatment. Now, we could run a frequentist or a Bayesian t-test and start to put some numbers on this to say how different are these distributions. But for this fictional data set, it's relatively clear that exposure to treatment is associated with increased outcomes. So can we say that the treatment improves the outcomes? Well, probably not. Because again, this is a simple scenario. Many more complicated ones exist, but in this one, we perhaps didn't account for the full data generating process that really underlies the data. So the conclusion that we came to through a purely statistical approach could be completely wrong because we failed to take into account this full data generating process. And in this case, we have a confounding variable, and this can be disastrous if you try to interpret statistical associations causally. So what can we do? We could use PyMC, for example, to translate what we think about the data generating process into code. So the exact lines of code here aren't important. They won't be in the test at the end. But essentially what we're doing is specifying what variables listen to what other variables. And because we are taking a Bayesian approach, we're also specifying prior beliefs over the strengths of these relationships. So the first step that we might take is to essentially run our Bayesian statistical inference, and we might obtain posterior distributions such as what we can see here. So we would essentially estimate the unknown parameters that govern the strengths of the relationships between the confounder, treatment, and the outcome. And because we are taking a Bayesian approach, rather than just getting a single number, a point estimate, we get a full Bayesian posterior distribution that describes the relative credibility of different values. Now, because this example is using simulated data, we can compare the model estimates with the true values used to generate the data. And that allows us to estimate how well this process is working. So looking at the one example that we've got here in the top left, we can see that the posterior distribution given in blue essentially represents a pretty accurate estimate of the true value of 1, which is given here in orange. And we don't need to go through all the others, but we essentially see for this example that is the story that unfolds for the other parameters in our model. But we want to do something causal. And one possible causal thing we could do is to calculate the average treatment effect. And if we wanted to distill this into a single sentence, we estimate this by basically asking, looking at the difference between what we believe the outcomes would have been if we intervened and gave everyone exposure to the treatment versus what we believe the outcomes would have been if we intervened and gave nobody the treatment. So we can do this in PyMC. We saw in the previous talk an example of the do operator. So PyMC recently obtained a do operator as well. And what this does is to take in a kind of a code representation of the structural causal model. You tell it what intervention you want to make, and then it spits out a new mutated model. And that represents your interventional distribution. And we can use MCMC in order to generate samples which approximate this distribution. Now, we can do the same thing for the case where we have no treatment, and then essentially just do the subtraction. So compare these distributions in order to come up with our estimated average treatment effect. And the plot here shows our full Bayesian posterior over the average treatment effect. So again, not only do you you can get a point estimate if you like. So let's say it's minus 0.0022, so very small. You get an entire distribution of credible ATE values. And we can see again, because I simulated this data where there's actually no direct causal influence of the treatment upon the outcome. We can see that by using this Bayesian causal approach with relatively few lines of Python code, we can get a pretty good Bayesian estimate. So our previous kind of statistical approach of, let's say, we could have done a t-test by just comparing distributions, observational distributions, was essentially meaningless. Taking a causal approach allows us to get a much better estimate, and taking a Bayesian causal approach allows us to quantify our level of uncertainty with the full posterior distribution here. And in general, knowing your level of uncertainty is really important, like I say, when we're making high stakes decisions about whether or not to roll out an expensive intervention. And in this particular case, we would probably decide not to do that because it has no causal impact on our outcome of interest. So in summary, we fully expect there to be a mass migration up the causal ladder as more people, companies, and scientific disciplines embrace causal inference. But we see many advantages that hopefully I've kind of outlined to pairing both causal and Bayesian approaches. And this is in terms of making the journey slightly easier, and also just gaining all the benefits of the Bayesian approach, not least the principled quantification of uncertainty. So we, as in the PyMC open source community, are working towards facilitating more causal inference to lower the barriers of accessibility to causal inference. Now, if you would like to know more, then we at PyMC Labs offer corporate training and consulting services using both Bayesian and causal inference methods. We've had the pleasure of working with some really fantastic companies and help them solve really hard but high impact business problems. And if you're interested in getting more of a flavor of Bayesian and causal inference methods, then my personal website has a set of recordings and also a list of the various kind of pedagogical, didactic writings that I've got on the topic. So thank you very much. Happy to answer any questions if we have time.
Thank you. We have a bit of time. So, and I will start first just answering people asking, is it okay to share public screenshots from all your great talks, like your bands and others? I don't think anyone will be against, so please do, and tag the event, and it will make us extremely happy. So I have a question for you. To use PyMC or causal pi, it is necessary to specify the formula that links each variable in the DAG. What can we do if we do not know what this relationship looks like? James, I hope I pronounced correctly, asks.
Yeah, so I mean that is tricky. So yeah, in PyMC, you do essentially have to describe not only the relationship, so the DAG, in terms of what is connected to what, but you also have to go further and essentially define a full structural causal model where you specify the nature of the relationships between those variables. So I don't have one short, easy answer for this, but it's going to basically be a mixture of starting simple. So very often people look at linear relationships. So you're effectively doing path analysis type stuff. You can introduce various nonlinearities if you have mixtures of like continuous versus discrete variables and so on. So I think this is the real answer, though, I think, is probably some kind of hard model building work, which involves exploring your data set and bringing domain knowledge about these relationships to the table. And you never know if you're correct.
Okay, and obviously Bayesian is a big topic and causal is a big topic. How do you think we can address the challenge of learning two approaches at the same time?
Yeah, so you're right. And I don't want to kind of shy away from that fact. So if you kind of start outside the Bayesian sphere and you start outside the causal sphere, then you could argue that you've got double the amount of stuff to learn. Now, but I believe in you. I believe people, you can do it. Yeah, what I would say is that personally, I'm kind of overjoyed if people take more of a causal approach, even if they stay like traditional. That's great. But yeah, we do see these advantages. So we kind of think that the payback is worth the effort. That's just been our experience.
Yeah. Brilliant. Thanks a lot.
Hello everybody. So it's a pleasure to be here at this Causal Inference Symposium. It's going to be a bit difficult to go after a big player like Uber, but I wanted to discuss here and to show you a bit our efforts in Total Energies on using causal inference to try to help our business. So maybe you don't know, but so Total Energy is a big company and we have very different type of influence in the energy, in the retail, in the renewable energy area. So it means we have a lot of data to deal with, and we need to help our business units with it. So in 2018, actually, we initiated a causality R&D project with three main objectives. The first one, which is not that easy actually, is to identify in all our business application where we can use causal inference and how it can help improve safety, operational excellence in the company, with a very strong focus on low carbon energies. Then the question on this is, do we need to develop our own causality technologies, or can we use the existing one? And then it will. The last part was to strengthen our competency through hiring and academy partnerships. So you probably know now, so I will go very quickly. But when we have data, we have different type of question we need to ask the data. So there is a big part, a descriptive part is data management, which is key, because if we don't have this, we cannot do anything. Then we hear a lot about more traditional machine learning, which is more on the forecast side for us. For instance, it's like you can predict how much a turbine or a PV farm is going to produce in the future. But a lot of the problems in operations are not traditional question, but are causal question. Like for instance, like why unit fail? What triggered it? Or what decision should I make to increase operational efficiency in this biofuel plant, for instance? Or is a variable A impact variable B? So these questions are extremely important for day-to-day operation, but are unfortunately not easily or are not answered by traditional data science method or traditional ML method. So I'm going to show you a couple of examples and how from those examples we progress in our thinking about causal inference. So basically, like the causal inference arrived in total like with two problems where it brought directly a lot of value. So the first one, so I'm sorry, it was like older, like legacy business, was for a gas field where we had like an EPC contractors proposing a new technology for the wells. And this technology was a lot more expensive, but when we looked at the well, they were producing more, like 30% more. And this is the point you see, like the dots you see in blue. And the question was like, is this technology worthwhile compared to the traditional approach, who was cheaper? And you see, for instance, like the wells here, the blue dots, for instance, not geographically placed everywhere. There is like cluster of them, and when you do the study, like those wells are in the better geology, so a bit deeper, with a bit better porosity, with higher pressure. And the question is to know, like from all those factors, is this new technology, like, is it playing a role, or is just what we see the effect of confounding factors? And we started like very, very easily. We use like propensity score matching, which is like the 101 of treatment effect estimation. But what we saw actually is this new technology was not bringing like 30% more production, but just like 10 or 5% more. And it makes like the use of this new technology not really prevent anymore for us. So it was the first impact. The second one is going to be actually presented in ADIPEC in Abu Dhabi next month, was about corrosion, and this has even a bigger impact, where we had like two fields, one with like nitrate that was injected and one without nitrate. So it was to control basically the bacteria in the field. And what we saw actually is that we had corrosion problem. The engineers had the intuition that the nitrates had an impact on corrosion and it should increase the corrosion. But when we looked at the raw data, they saw the opposite. And for them, it was very puzzling because they needed to give recommendation on the steel tubing they need to use. And it was not like what they saw in the data was not consistent with what they think they should have seen. So they were very confused and they were not able to give recommendation. And so we did the same analysis, like very simple propensity score matching. We tried to find like two populations with like the confounding factors effect was kind of minimized. And what we saw is that the field actually with nitrate injection had a lot more corrosion than what we saw in the raw data, in the raw comparison. And I didn't show the slide like it would be the presentation, but also a lot of variation in this subgroup you see in green here. And this was like indicate them that this variation is probably because there is like effect of bacteria in it, and they need basically they had to investigate more. But the result of this analysis basically and the extra analysis, the extra work they did, allow them to really specify the right steel tubing for the right field and the right properties. And it has had a huge impact on the basically on the corrosion they saw in the field afterward. So we started with these two simple example, but we had the feeling in the last one that there's probably other factor. There is a heterogeneous effect of the nitrate on corrosion, and maybe we need to dig a bit deeper on causal inference method. And so what we see is the heterogeneity of the treatment effect is how we can deal with it, because in real practice, basically, we need to really pinpoint the right population to have the right treatment. We cannot like do blanket statement like we use this steel or this technology for the entire field. In general, it's too expensive. So we really need to have this heterogeneity of treatment effect. And the other problem is also that in general, like treatments are not binary. So in our like nitrate injection, for instance, you can have like the concentration of nitrates that also impacts the corrosion. And the question is, how can you account for this in your causal inference study? And so you can actually find like all those graphs in a paper published by my PhD student, Naoufal Asharki. And so we started to dig a bit more, and so it's going to complement the previous talk. We started to look at the different methods for heterogeneous treatment effect. And we had quickly a problem, so I'm going to put here, is like we have data scientists in total, but they are definitively not experts in causal inference. They have a lot of work for cleaning the data, and they didn't really have like the time. Like it was very impressive for us and them to have all those choices of causal inference use, not knowing how to choose them. So the approach we decided to go was more like to go with meta-learner and saying, okay, forget the type of algorithm you're going to use. We are more going to try to specify the right frameworks to use the algorithm you want. So it can be random forest or XGBoost or neural network, but we are going to guide you on the meta-learning process you need to use. And the problem, so to come back to the previous talk, once you say this, you need to validate the method. Like it's very difficult to give recommendation if we don't know, if we don't have a base like result to say, okay, this method perform better. And so what we did is the creation of a semi-synthetic data set. So it's a huge data set. We use like a physics-based simulator, and so we simulated basically a geothermal system, like an enhanced geothermal system, where you have a wells going like in metamorphic rocks. You have like some fracs, but you have different design of fracs. You have different conductivity of your rock. So you have many factors that can impact the heat performance of your wells. And the idea is to emulate basically a real-world situation. From this data set that has bias, that is trying to be as realistic as possible, try to isolate the effect of each factors. And then, since we have the ground truth with the simulation, to compare how the meta-learners perform versus basically what's the real effect, the physical effect of this. So we cannot, it's too difficult, we cannot validate like causal inference in real data sets, but we try to get as close to a real data set as possible. So I think we generated like probably like 300,000 simulations with different configuration. And from that, we extracted like some set data set with bias, like confounding effects and so on, and try to assess the efficiency of the algorithm. So it's the same, like the data set is public in the GitHub of Naoufal. And so what was very very puzzling, it's still puzzling for us, is that we had a lot of variability in how the meta-learners were working. And it depends on if the treatment is continuous, or if there is multiple treatment, or if we have binary treatment, how much data we are using, how much like confounding bias we are pushing to the data set we are creating. So we had this table. Then now we need to work on it. What was extremely surprising for us when you, the most difficult case, so continuous treatments, the meta learner who was performing the best actually was the S learner. So basically just one model and you train on all the data. And for continuous treatment, it seems to be it's not ideal, but it seems to be quite robust. And actually it's what our data scientists were doing. So yeah, so you have the name of the publication. So it's actually, it was published, I didn't change it. It was presented at ICML this summer in Hawaii. So this is like, so we worked on this, and then we had like a business unit who came with even more challenging problem, and we didn't like this one. We're still working on it, but we are not. We are not there yet. It's like the problem of multiple treatment effect, actually multiple like continuous treatment. And the use case actually is extremely important for offshore wind, and it's the problem of welding. So like when company like Total or BP, they create like offshore structures, they need to design like to optimize the weld strength. And the weld strength is dependent on many factors, the voltage you're using, the temperature, the amount of carbon in the steel, and so on. So you have maybe like 50 parameters to use to try to control the yield strength. So what we want is not really like, ideally, we don't want to predict your yield strength. We want to find the best combination that optimize this yield strength. Simulator is such a complex phenomena, welding, that we don't really have good simulators. So we need to rely on the data. The other alternative is to do many tests in laboratories with different configuration, but this is expensive. It's probably like, each test is probably like $5,000 or $10,000. So if you need to do like 1,000 lab experiments, it's too expensive. So we try basically to work on this multiple treatment effect, and it was very difficult. We used the deconfounder, who was not performing very well, and so we decided to go two-way basically to launch a postdoc with a French school to try to experiment different method, and then we are working with Causal Lens also to try to see with their approach with more graph-based to see if we can solve part of this problem. So this is for the treatment effect, but we also have the problem of time series. And so we divided the causal part of time series is in two. The first one, which is, I don't know if it's traditional causal inference, but it's like root cause analysis. So for instance, if you have a failure on an equipment, so it's very good to be able to predict the failure, but at some point, the operator is going to come and ask, okay, what triggered this failure? You know, like is there like a change in variable? Did we move like a valve or something like this? How can we see where it's coming from so that we can avoid it next time? And so basically, for this approach, we use something inspired by epidemiology, and it's the case crossover design. And we mix it with association rule mining. So it was published in 2021 in KDD. And the idea is to look basically just before an event, what was all the variables doing, basically, and compare them to like a normal period where we didn't have this problem. And doing this, you can like compare these two populations and see what are the key differences. The association rule mining goal is this, basically, is to identify what varies between these two time periods. And it's quite powerful method to do this kind of study. So we use this for equipment failures. We can have a look at the paper, but then, and so we are still working on it, or the team is still working on it. From there is, okay, now we want to predict something, but we would like to predict in a causal way so that if we change in the input variables, is really the causal effect that is that impact the forecast and not just like a correlation. And it's something where like a PhD student is still working on. That is not like it's starting to be closer to reinforcement imitation learning, but it's quite challenging. So I just like presented very quickly our different problem challenges we had, but we also had some key lesson learned. First of all, is like causal inference is like important. Like clearly, it can answer like very like business question with huge impact. But it's very hard because you need to ask the right question in the data. So you need to have your domain knowledge expert with you, like to analyze the data. We still have room to validate the causal models. So when we have a result, we need to go back to the experts and ask, okay, does it seem relevant to you, this kind of results? So it's really critical to involve people that are not necessarily data scientists. So you need proximity with this kind of people. What we found also is that epidemiology approaches were like a very good first step with us. It's very pragmatic. It's easy to explain to the domain knowledge expert. There is an intuitive part of it. And so we did very good. We have very good progress with this kind of approach. And I want to mention, like, so we are not a big tech company, so we don't have a population of data scientists like Uber or Google or Amazon. So it's a lot smaller. And then what we need to remember also is to show the added value of causal inference, because we are always going to be challenged. And why I'm just not doing a forecast, maybe it's good enough, and this kind of challenge comes very often. So we need to show that using a causal approach is important. The other part I was quite surprised is we didn't really have a lot of demand to work on causal graph. And I'm wondering if it could be a good collaboration tool for the future. What we saw is that in general, like the causal graph was known, and it was really the effect of variable that was the question. But maybe we will find some application in the future where we need to draw a new causal graph, because what's missing. And the last part, and I think it's very important, is with the new AI Act in the EU. What I showed you is like causal inference really to assess the causal effect of variable, but there is a part of causal inference that can be used for explainability. The models are more robust. We ask very clear question to the data set. We can use causal graph, for instance, to represent what we see in the data. So I think there is a lot of work to do to use causal inference or causality or causal discovery for explainability. And the last part, so what I showed you is not like it's really a teamwork, because we collaborated with a lot of people. So like school in France, but also in Germany, and we also have a common lab with EDF and Thales where we developed many of these methods. So thank you very much.
Thanks a lot for your presentation. We generally, how it says, we moved from theory to practice. So yours was really practical one. And I'm sure people learned a lot of lessons.
All right. Hello, everyone. I hope everyone can see us as well. So this is, I think one thing which, before we get started, introductions and everything, I would say that the discussions we've been having, or the actual topics and some of the technical details that have been shared in the last 3.5 hours, I personally found to be very, very useful. I'm hoping that everyone who's attended it has also found it to be useful. And this is the last session, and then we have a wrap-up session from Fran after this. So what we want to do is actually probably talk about some of the key challenges or key questions which we think are going to be quite key in implementing causal techniques in our day-to-day activities. So I guess that's where the theme is coming from. I guess I want to do a very, very brief intro to the panel here. So I'll get started. So my name is Harsha. I am the head of data science and AI at BP. I'm been working in this area since I got my PhD in Austin, Texas, from computational mathematics for the past 16 years. So very excited to actually be part of this panel with Candice and Lars. So Candice, do you want to go next?
Sure. Thank you so much for having me today. I'm Candice Hogan. I lead our carbon neutrality department at the Toyota Research Institute. And here we bring together behavioral science, machine learning, and human-computer interaction research, and of course, causal inference into our work. I'll pass it to Lars.
Thanks, Candice. Thanks, Harsha. So my name is Lars Kunze. I'm a department lecturer at the Oxford Robotics Institute at the University of Oxford in the Engineering Science Department. There I lead the Cognitive Robotics Group. We are mostly interested in scene understanding questions for robots, causal inference and explainability. But I'm also the technical lead of the Responsible Technology Institute. So this is where we're trying to bring in the technologies and deploy them in society and looking at more kind of ethical and social questions as well.
Fantastic. Thank you for doing that intro, guys. I guess but let's start with this very simple thing. I think just to sort of warm ourselves up. So in what way do you sort of use causal techniques in your day-to-day activities? What excites you the most when you actually use that? I know it's a technique, just like any other technique. It sort of helps answer a question. So what sort of things are you looking at?
Absolutely. I'm happy to share a little bit. So in our work in carbon neutrality, we're really focused on helping to identify ways that we can enable Toyota customers to contribute to carbon neutrality, to reducing carbon emissions. And in particular, how can we help them to transition, for example, to electrified vehicles? How do we understand things like the usage of charging infrastructure or challenges with charging infrastructure in different places? And so by using causal modeling, causal inference techniques, we're able to compare different potential interventions that we might consider to understand what the impact there might be. And that then helps us to build novel technology to support customers in that way.
Got it. Thank you, Candice. Lars, if you want to share something, I'm going to ask a question to Candice afterwards as a follow-up.
Yeah, sure. So I think from our point, so in robotics, so we are trying to embed causal inference and causal discovery techniques in all kinds of different applications, from assistive to collaborative robots, autonomous driving, inspection tasks, exploration, using drones, or even space applications. So I think there's a broad spectrum, because I think causality, that's very inherently present in robotics. So we often think of in robots kind of as a sense, think, act paradigm. And so we have all these observations. We need to do reasoning with these things and then decide what to do best next. And so we are using techniques for planning. So some of the work we're doing is more geared towards policies and decision making for robots. And the other thing is more behavior understanding. So how can we can get better estimates of what happens around these robot systems. So I think, yeah, all of these kind of techniques that have been discussed today are quite valuable for us, and we try to cover quite a spectrum of applications.
Fantastic, Lars. I think you sort of touched upon the area which I was keen on getting both of your views on, which was I think forming and then informing everyone about the policies is a very, very challenging area, especially when you talk about AI or machine learning and sort of the apocalyptic messages that we keep hearing every day, which I guess partly we do have to fear the Terminator, but we don't have to do it in the next few decades, I'm hoping. But I guess the question comes back, can causal techniques help us fill the quantitative gap? I wouldn't say it's a complete gap, but quantitative sort of a little bit of a gap to make a bit more data-driven policies when it comes to wide applications of AI/ML. Have you seen that in action, like how you were mentioning both in your day-to-day activities? So Candice, I guess you can.
Sure, absolutely. I definitely think that causal inference helps us to fill a gap because it enables us to leverage observational data. It enables us to to test potential interventions that we would otherwise not be able to test due to cost, due to time, due to safety, or potential legal ramifications. So it enables us to understand, potential alternatives that are otherwise completely inaccessible to us. And then that helps us work toward those possible futures, to understand which possible future is worth building toward.
Cool. Thank you, Candice. Lars.
Yeah, I absolutely agree with Candice here. So I think sometimes, in particular in some robot applications, when we're considering driving applications, so of course we cannot really intervene in all in our actions because it's a safety critical application, and so we have to rely on observations that we can make, but then we can also bring in counterfactual reasoning and simulations in that space. So this is where we can really leverage the different levels on the ladder of causality and use these reasoning techniques, because sometimes, we are really constrained in terms of what we can do in terms of experiments. And also the other thing is maybe the leveraging causal inference for explanations and explainability. I think that's super important if you think about accountability of these systems as well. So I think that this is another huge benefit that these methods can bring.
Fantastic, Lars. I think it's as if we've discussed it before and decided on a theme, because the next thing that we should be speaking about is can you help us unravel the intricate relationship between causality and explainability? Does causality actually imply explainability? And what happens in the situations wherein when we're not able to measure how much we don't know, even before we measure how much we know, I guess. That's a bit. So I guess, Lars, because you touched upon that, if you can sort of give your view on does causality really explain or imply explainability?
Yeah, I think causality is super useful. In particular, as I said, so we're looking at the different steps on the ladder of causality. So I think we already heard in Judea Pearl's talk this morning or earlier, kind of the different tools that causality brings in terms of transparency, testability, attribution, explainability. So I think these are things which definitely can help us and to address questions of bias, fairness, and so I think it really is a beneficial tool here. So we are looking at this in the context, for example, in accident investigation, where we really want to get explanations out of the system. So we want to ask the system queries like an accident investigator would. So why did this happen? Why did you do this, robot? Or what would happen if? So these are questions we're quite interested in. So we are bringing in also natural language models into that. So we're going from natural language questions, trying to resolve them on a more technical level, and then getting these answers from on a more mathematical basis back, and then translating those back into real world or natural language. So I think, I think for us, it's a fundamental tool for providing explanations.
Fantastic. Thank you, Lars. Candice.
Yes, absolutely. So I think of explainability in a couple of different ways. So one, as Lars was discussing, we can use causal inference techniques to help us kind of peek under the hood, understand if what we think is going on in a process is supported by the data, if that is truly the path that we're taking. Another way, causal inference is helping us understand why something's happening and not just what is happening. It is helping us understand that why, but how easy that why is to understand. We shouldn't forget that the relationship or the causal map can still be really complex, and it's not going to be completely clear necessarily, depending on what the domain or the process is. So simply having that causal map or that causal analysis will give us those relationships, but as a human, we still may not be able to quite understand where all of that complexity is.
Awesome. And I guess tying back to one of the questions I was asking earlier, how would you actually is it possible? So say, for example, I think one of the questions which was completely recurring throughout the sessions today was the whole fictional notion of a subject matter expert. I fully don't agree, but I guess I can relate to some of the pain points that other practitioners have felt. And they also talk about do we have to start with a DAG for that? I mean, do you have to start with a graph that we need to create? We need to work, we need to understand the business process to actually come up with the actual graph and all of it. And the constant question is, can we not auto-discover it? Like, are there techniques which can actually auto-discover it for us, at least give us a starting point? Now, my question is not really about the auto-discovery part, even though we can get into it if we have time. My question is, even if we start with the best known assumption or best known graphical representation of the subject matter expert's experience, how could we quantify what we don't know? I mean, I mean, again, we go into the realm of experimentation, but how have you seen those sorts of unknowns sort of being quantified? Or at least we don't know what those things are, but we're saying, oh, we're definitely missing this. We're missing something, right? So I guess, Lars, if you want to kick us off.
Yeah, I think it might be easier to start with the known unknowns, kind of trying to estimate those things. So, for example, in robot applications, we often work in a dynamic environment, and we have this open-ended world assumption, right? So that there are things that will happen to us kind of during the lifetime of the robot that we cannot really anticipate. But there are, of course, some known unknowns. So we maybe don't know what objects we have to deal with, but we know that these kinds of objects maybe in our everyday lives. And so we can make some assumptions at least about these things. And maybe this is something which we can learn from experience, how many new objects come into our robot application every now and then. And so we can build other models which trying to make predictions about this. So I think if you have some statistical data about this from past applications, so you can maybe build predictive models, and that can give you some sense of this, what you don't know at the moment. For the unknown unknowns, of course, that's much more difficult. So I hand this over to Candice.
Yes, if only there were a simple answer. I wish I had the answer. I think one of the fun topics that we had discussed in our previous conversations leading up to this chat was, what keeps you up at night with regard to causal inference. And I think, that, like, what are you missing? And really, when we're using these techniques, oftentimes, as we discussed, we're using them in situations where it's not possible to, run a randomized controlled trial or to kind of validate in those more typical ways. And the stakes can be high, and that makes it dangerous. What you don't know matters, and oftentimes we may only find out when there has been some type of negative outcome, right? These are the things that we hear most about and the things that we dread. So in addition to, Lars' comments, I think I would just also say, considering what potential guardrail metrics or outcomes you might keep track of as you begin to implement based on what you have found. Are there any ways that you can validate if something is going wrong? Like, what is accessible to you? Is the best that we've gotten so far.
Awesome. And I think for me, the reason I was asking that question was because it is a difficult question. I think as practitioners in this space, some might feel a compelling pressure from their stakeholders or managers who are sort of sponsoring the project to sort of actually say that this is 100% accurate, or get to as much percent of accuracy as you want, and almost write the whole AI unfortunate promise that it's going to solve everything. So I think the reason I was actually discussing or bringing this up is to just say it is not an easy thing. So no one will ever know that. So it would be all right for people who are practicing in this area to push back saying, we can get to this thing, but there could still be a lot of unknown things that we don't know. So don't make your decisions blindly on the basis of this. Use your intuition, use your past experience to do that. And I guess that's what I was trying to sort of tease out of it. Go for it, Lars. Yeah, I think I would, totally agree with also what you said and Candice. So I think in the end, we're building a model, right? And kind of in some sense, it's kind of a level of abstraction we have kind of decided on in the beginning. And so it's definitely going to be wrong at some kind of level. We're making some assumptions. So that was clear from one of the talks earlier today. We have maybe biased data feeding into this. But I think critical also what Candice said is kind of we want to monitor what's going to happen while we are using it and kind of maybe improving it over time. And I think the kind of transparency that comes with these models is great for doing that. So we have something we can track actually and monitor. I think another challenge in that space is also who is actually going to build the model in the first place. So is it industry or does it come with some kind of regulations from the government or kind of, so I think that's also an interesting question to consider. No, absolutely. That's a fair point. I guess we can actually extend it a little bit, right? Now, with the whole thing around the AI regulations, which are happening all across the world. I mean, in the last few months, in the last few years, we've been seeing like more than 120 or 150 laws being passed, or no, I wouldn't say laws, but close enough to being legislations, like being passed and considered. Where do you see newer techniques or techniques like these, like causal techniques, help us protect organizations, protect consumers, say for example, from making from maybe irrational, uninformed decisions from organizations or governments? Have you started seeing this trend in the US and UK? I guess you Candice, you're in the US, and Lars and I are in the UK, so we can bring that view. Are you seeing those conversations kick off in the USA, for example, Candice?
That's a great point. I think definitely around AI safety and ethics, many conversations, and of course that will necessarily entail many types of modeling, because anything can also be referred to as AI in some ways. So I think there are those considerations, but as those talks are happening at the policy level, and of course we see this often, policymakers or folks in that situation having the best intentions to protect consumers and to ensure creating a safe environment, aren't practicing with the data and may not understand the challenges or even the biases that those policies then create that aren't already existing in the data. So it's creating new issues. Now, those can be some of your known unknowns, because at least we're aware of what the policies are, and we can have an opportunity as the laws are passed to track how things change. When you implement this policy, how is that influencing the causal paths that you have previously identified? But I think it's going to be a continuing evolution and a continuing challenge, and something certainly to stay close to. And I'm very interested to hear how things are going in the UK in this regard.
Cool. Lars, you want to take us away, and then I'll add?
Yeah, so I think in the UK there is kind of one of the larger programs which was initiated by UKRI, so is the TAS Hub, so Trustworthy Autonomous Systems, so which looks very much at the kind of technical development, but also governance and policy issues around that. So there are different nodes where different universities and as well as industry partners collaborate and kind of really in a multidisciplinary way. And I think that's really key. That's a program where I also leading one project where we're looking at the use of responsible AI, and in particular for the long-term deployment of these systems and what happens if something changes either with the system itself or the environment. And this has been now followed up with another program on responsible AI, so AI UK. So this is a new program with, I think, 30 million government funding to unify some of the projects in the UK. So I think there is a huge push towards this.
Yeah, totally agree. And I guess the whole the EU Act, the AI EU Act, which probably is going to actually become a very strong law or legislation by 2025, is actually just like GDPR. I think it's actually is one of the most stringent AI sort of governance, sort of legal issues, legal setup there. So almost all organizations have to start thinking about it if they haven't already. And I guess different organizations have different levels of maturity. We have been thinking about it for a while, working with Oxford and and MIT and others in this space. But I think it depends on how you think about and what sort of use cases or what sort of things you want to actually do with AI. I guess that's where the thing is. Okay, I'm going to ask a very simple question, and then I think we're receiving a few questions from the audience as well. So we'll try to accommodate them. If someone wants to do good, robust application of causal inference or causal science, any of the causal scientific techniques, do you need a lot of data, or can you actually get started with very little data, or examples or use cases where you don't have a lot of data, but you still want to understand very strong relationships? Candice, do you want to get us started?
What's a little data and what's a lot of data? That really depends on that depends on the field that you're coming from. I'm an experimental psychologist by training, and many of the experiments that we run, 100, 300, 500 participants would be considered a large sample in some cases. Yeah. And so I think that it really depends. It depends on how much variance you have in whatever data you're measuring. And of course, the greater the variance, the larger the sample size you're going to need to support it. The greater the complexity of the model, the larger the data set you're going to need to support the analyses that you want to do. But ultimately, if you need to understand something about causality and you have a smaller than preferred data set available to you, it becomes, one of the points that you acknowledge, one of the limitations of the work. And perhaps when more data become available, you can replicate in adding those in.
Cool. Thank you, Candice. Lars.
Yeah, I totally agree with Candice. I often find it quite useful actually to have only little data available, because then you can try to understand the causal complexities or kind of the relationships behind this kind of maybe even better. Kind of working on very small examples as a proof of concept is often very helpful, at least in research, and then building onto that and expanding from there when you have more data available. Yeah.
Got it. Fantastic. Thank you. Okay, so let's take one question from the audience. I have it right here. So Jeremy Loscheider, I think he's asked a question. I'm going to read it verbatim. So taking my cue from Harsha's question about the Terminator, how can causal AI enable us to shift the conversation around the use of AI in the future, especially among non-technical audiences? So I guess it's the usage of causality as a tool to demystify the application of AI. Candice, you want to get us started?
Sure, absolutely. I love the question. I think that's exactly what it is. It's demystifying. It's helping to explain what's going on. I think when people who are not part of AI or part of any type of data work are exposed to these things, and especially exposed to media around them, it can become frightening, it can become scary. And so if we can help to reveal what's going on, or provide more clarity about what's going on, then that can help to ease some of that concern.
Got it. Thank you, Candice. Lars?
Yeah, I think that can definitely help kind of to understand the problem. I would say also in general, when you're tackling these problems, so often you want this kind of technical expertise, but then you also want, of course, kind of the domain expertise with that. So I think you always need these kind of two sides, right, to bring together. And I think, for example, in Robert's talk, we saw maybe how also ChatGPT or these tools could be used as a mediator to try to build these models, kind of initially, even if you don't have the technical background, you're coming in as a domain expert, you're building a model. But then, of course, you need the technician to verify this. So I think this communication is super important. So yeah, I don't think that kind of ChatGPT will be able to do everything out of the box, and we should maybe do this. I think Robert also alluded to this because of the danger that comes with it. But so there's also the great potential to utilize these tools for communicating and bridging the gap between the knowledge. There.
No, I mean, I sort of completely agree with you. I'm going to probably just add or sort of restate what you already stated there. So for me, one of the biggest things around the application of AI is around, I would say, an education program around AI. When we talk about specific organization, I think within the organization, you need to actually have senior leaders as well as everyone in the company who is trying to use AI. Have a good level of healthy relationship or an understanding of what AI is, what it can do, what it cannot do, where you should be cautious, where you don't have to worry about things, all of those things. Now, so causal AI becomes more like a specific technical strand or a technology strand for anyone in the practicing area of AI. And then I would say, because explainability becomes very much of an issue, you trying to sort of measure the effect of an action that the business can take. And if someone says, I can give you the exact quantitative impact of the effect you're taking, the business is all over it. But again, for me, going back to the whole thing, especially in non-technical audiences, I usually am the party pooper in all of those things. I basically start by saying, don't assume it's going to answer anything. It has an uncertainty. It has a certain level of certainty in it. So take them as directional. Sometimes if you get too good a result, I'm going to be absolutely scared. Sometimes if you get a very bad result, I'll be like, that actually tells me more, because a lack of stuff is also more information than uniform distribution, like we all know. So any sort of distribution other than uniform is the best way of finding information. So I would look for those kinds of insights and actual conversations. I guess that's one way to take care of the use of this, I guess. Cool. Let's take another question. This is coming from Alexander Mulak. So people often ask about limitations of causality. He wants to reverse the question. So he's asking us, what are the best success stories using causal models? So Lars, do you wanna if you can pick one, what would that be?
Best success stories.
I can sort of get started while we think about that. So for me, I think there are certain areas. So as an organization like BP, I think BP is a company which is made up of many different entities and businesses. So each area has its own sets of questions, own sets of problems. I would say one of the best stories would be measuring the effect of a particular intervention that we have done. I can't reveal it completely because I checked with legal to say if I can actually reveal it, and they're like, no, you can't. So I'm just keeping it at a high level. But we have a very strong market differentiating application of causal techniques in which we are sort of testing out multiple interventions on one of our key work streams. And we are able to quantitatively measure the effect of that even before we run an A/B experiment. Now, in some instances, we've actually sort of not seen favorable results. In other instances, we've actually seen favorable results. But overall, when you look at the average effect, what we're seeing is that we are able to inject some sort of a robust or explainable uncertainty into what we're doing in the market. So we are not sort of losing anything out, but at the same time, we're sort of maintaining advantage. I know it doesn't really help Alexander with my levels of abstraction, but believe me, I've tried really hard, but yeah, couldn't get the approval. So Candice, do you have anything that you could share?
Yes, and I think it will be similarly not quite satisfying, because I will have to keep a similar level of abstraction. But actually across companies where I've had the chance to be part of the causal inference work that's going on, it has enabled teams to gain traction on otherwise intractable areas, things that you cannot measure directly, things that are unsafe, unreasonable, far too expensive, takes too long to conduct an experiment. And what that also does by making an intractable problem in a way tractable, helps to explain the value of causal inference, and it helps to get buy-in and support from especially higher level stakeholders in organizations. And then once you have that support, you can start becoming part of the process. So really, I would say that's what one of the biggest success stories is having a problem that is so hard no one else wants to touch it because the other modeling approaches are not appropriate for it. And then you get a chance to apply these types of techniques. You can show some impact, and then you can start building out your program of causal inference where you are.
Awesome, thank you. We have another question. So let's see. Sorry, sort of losing my thing. So this is again this coming from Jeremy again, one of the first question asker, and he's asking from the perspective of a newcomer to the causal space. It's often causal inference is often referred to as being a superior method to association-based approaches. And his question is it really true? Have you found that causal methods are a true replacement, or is there still a use for association-based techniques? Lars, do you wanna give your view?
Yeah, I would say it's kind of a complementary method in that space. So we definitely maybe want to use, and of course, kind of statistical methods and deep learning methods for in particular machine learning is quite strong in prediction approaches, which are based on associations, right? But I think the methods can offer kind of maybe a different perspective, in particular if you're thinking about interventions or counterfactual reasoning. So I think, yeah, it is complementary in that space. So I think in one of the talks, we saw this kind of diagram where we have the ladder of causality on one axis, and then the level of uncertainty maybe we have to deal with. And then, so where you kind of are, where your problem is based in that space, maybe this is kind of where you choose your method from. And yeah.
Cool. Candice.
Completely agree with Lars. You know, causal modeling methods are a tool or a set of tools in a much larger toolkit. There's certainly many applications for association-based methods, and you know, don't go after a problem that for which a hammer would suffice with a jackhammer, right?
Absolutely, and I guess I say completely. I believe I fully believe that any of these techniques, these are new techniques, which even the whole advancement in the generative AI stuff, the building of the really large language models and everything, I always think of them as one of many tools that you can actually use. In most instances, for one to answer a question, you could probably, if you're good at statistics, you could probably get an answer 80 to 90% there. Now, of course, there'll be other things of saying, oh, how do I get the additional 10%? Because that's where all of my value is. So you actually start doing other things. So I would look at causal AI techniques or causal inferencing techniques in a very similar way. I would think of them as something that you need to use along with other things. I don't think just because you have a technology, go beat all your problems with it, because that's never going to solve anything. So I guess that's where I would probably stop saying, okay, there is a place for all of the techniques. There isn't a bad or a good technique. There are different areas where you can apply those techniques. I think that's what it is. Cool. I think we are on time. Thank you so much, Candice. Thank you so much, Lars, for actually joining the panel. I've really enjoyed this session. I'm hoping that everyone else has as well. And yeah, thank you. And we're going to wait for Fran to sort of wrap up, and then probably, yeah, that's it.
Thank you very much, Harsha. Thanks.
Yeah.
Bye, everyone.
Bye-bye.
Hello, everybody. I'm glad to be here and to tell you the miracles of counterfactual logic and its applications. What I'm going to talk about is outlined here. These will be, I begin with the overall view of what causal inference is about and what counterfactual logic is about, and then I'll go to the area of application. So my starting slide will be 3 slides in which I give you the 3 basic things to know about in causal inference. The first will be the 2 fundamental laws of causal inference from which everything can follow derived mathematically. Then I'm going to talk about the ladder of causation, which is the product of the first 2 laws. and some people call it the double helix of causal inference. Then I'm going to show you the third slide, which will be a summary of 7+1 tools or pillars of causal wisdom. These are the type of applications that we have encountered so far successfully. Then I'm going to talk about the +1 application, which is a personalized decision making. That will be the applications part. And here I'm going to talk about how the personalized decision making is different from population-based decision making. I'm going to show you how it is estimated to select patients in need, and that will be the type of application I'll be focused on. And then how we estimate personal benefits and harms of a treatment, and how we use to discriminate those who benefit from those who don't. So let me go first to, as I promised, to the two fundamental laws of causal inference. When we talk about causal inference, we have to have a model of reality. A model of reality will be a collection of functions. It tells you who listens to whom and what is by what response. The graph will tell you qualitatively just who listens to whom, but not how. The model of reality is more specific, tells you what the response will be after listening. So imagine that you have a collection of functions, tell you that A responds in this way to B and to C and so on. Just a huge collection of functions. The law of counterfactual said if you want to find out what the output Y would be, had X being a variable X being equal to a constant small x, for any unit, I'll tell you how to compute it. Simply go to the model itself, mutilate it, and make it an M sub x, and then find out the value of the variable Y in that mutilated model. Once you do that, you get the correct answer to your question, what would Y be had X been X? So what I've explicated you in what I call the law of counterfactual is how to treat the connective had X been X. What would be the, for instance, how many years would you live had you smoked 5 packs a day? I'm saying had you, that connective, called counterfactual connective subjunctive mode, has not been formalized in science before. I'm doing it now. And this is all I need to know when I compute both interventions and counterfactual. This connective that you see in subscript here is the essence of what causal inference is. So look what I've just stated here. I stated that once you have a model, it generates and evaluates all counterfactuals, no matter how complex, no matter how time it is nested. You can have a truth value assigned to every counterfactual statement. Keep it in mind, it's algorithmatized, and that is all one needs to mathematize causal inference. A derivative of that is a second law, which tells you that once you have, if you don't have the model itself with a collection of functions, you only have the graph, which tells you who listens to whom, you can say a few things about the model and about the data. What you can say is something extremely powerful. You can say that if you find separation in the graph, here, so if X is separated from Y, imagine nodes there, and you have 3 sets of nodes, X, Y, and Z. If the set of nodes Z separates the set X from set Y, then you should find a conditional independence in the data. And that allows us to do marvelous things like to test models, to test compatibility of data with models, and many other things. So I put it down as 2 fundamental laws of causal inference. Once you have it, you have mathematization of your reasoning. What does it mean, reasoning? It means that you come to the computer and you ask, computer, computer on the wall, this is what I know, and this is what I want to know. All mathematics. Tell me if I have enough information to answer what I want to know with the data that I have. And I'll tell you what kind of data I have. I can have experimental data. I can have the contaminated data. I can take selection bias data, or I can have observational data. I'll tell you what kind of data. I'll tell you what I know and what I want to know. And you tell me if I have enough. If I have enough information, then I want to know the answer. And the query that I want to know, of course, will be also articulated in the language of counterfactual. Okay, I'll give you some examples and we'll go. A derivative of that mathematics is that we find that we have three kinds of sentences or set of sentences. In the bottom, we have what statistics is giving us, and this is associations. This is what you find in the data. You don't need to have a model for that. You just have to have a data. If I see X, I can tell you how likely is Y. And this is what machine learning is giving us, and this is what deep learning is giving us, and this is what classical statistic has given up so far. If I see how likely it is, how likely is a given outcome. And this is, I put it down, owls and snakes, because they have developed a very powerful vision system to tell you what to expect next, like where to find the prey if I am a hunter. Now, intervention is a different mode altogether. What is special about the hierarchy? The hierarchy is set of expressions. Each level you have set of expressions of a certain type that is powerful enough to tell you everything below it, but not anything above it. So here I'm going from ladder from a rank 1 to rank 2, from seeing to doing, and here I can answer questions of greater complexity. What if I do X? What if I stop smoking? What if we ban cigarettes? If I take an aspirin, will my headache be cured? What, and so on. That is the effect of intervention. These kind of questions cannot be answered by seeing alone. Statistics proper cannot answer this question. You need to have additional information that comes from where? From the model. Sometimes the graph itself is sufficient. Sometimes you need the functions behind the links in the graph. The third level, which is the building blocks of science, it's imagining. It's answer retrospective question. It has everything that you ask for when you are saying that you understand the thing. Then you understand the thing, then you can answer a question about was it Y that caused, was it X that caused Y? What if Y had not occurred? What if Cleopatra nose were differently, of different length? Would history have been developed in the same way? What if I had acted differently? Was it the aspirin that stopped my headache, or maybe a good news that I received? Would Kennedy be alive if Oswald had not killed him? What if I had not smoked the last 2 years? That means, and why we call it counterfactual? Because it has a contradiction with what we see. The question contradicts what we actually see. I see that I now have cancer, and I ask myself, would I still have cancer had I not smoked for the past 2 years? Where is the contradiction? I ask about what if I didn't smoke, and I know that I have cancer. So I'm hypothetically causing a contradiction between what I know about myself and what I'm asking about. Okay, this is very important thing to keep in mind, because once you have this hierarchy in mind, and that's why people call it the DNA of causal inference, you know what you can do with the type of questions that you have. You know where to seek the information, at what level, what type of data you need to in order to answer the question. Okay, I'm finished with the hierarchy, and I go to the 7 pillars. The 7+1 pillars or tools of causal inference that I'm going to summarize for you, just to give you an idea of what have been accomplished in the causal inference scene. And I will then focus on the 8th one, the personalized decision making. What we can do is to encode causal information. I'm going to one by one now and elaborate on each one. Encode causal information in transparent and testable way. And here I'm talking about the graphical language. Encode it in transparent. Why is it transparent? Because we can communicate with the graph. We can share what we know, and we can also test what we know against the data. So that is a powerful thing about the language for articulating what we know and deriving what we want to know. But here are the typical things that we want to derive from that. To predict the effect of actions and policy, we simply turn the crank and let the algorithm produce answer to queries of the type, what if we ban cigarette? Of what if we take a certain treatment as opposed to another, or a policy, what if we impose tariffs on imports, and so on. The third tool is computing counterfactual, which needs level 3 of the hierarchy, finding causes of effect. Damage was done. Where do we attribute blame and credit? Can we explain why things happened? And this is a level, the tool which I call attribution. It's a very important tool in legal reasoning. It's very important in diagnosis and troubleshooting. I'll go to level 4. Each one has a different, by the way, each tool that I'm talking about has a different set of tricks and algorithms, because it's a different kind of type of queries to which we seek answers. Computing direct and indirect effect, which we call mediation, or separating the direct from indirect effect, is extremely important for questions of discrimination, for deciding fairness or inequities, because in many cases it is the direct effect that tells you if discrimination has taken place, and not the indirect effect. For instance, in employment discrimination, if you discriminate, by sex, for instance, you're not responsible if you are discriminate on the basis of quality. So quality will give you an indirect path between the hiring, between the type of a person you see and the salary he or she receives. But the direct effect is many times forbidden by law, which we label it discriminating, which is we forbid by law. So we must, in this kind of application, separate between the direct and indirect effect, and that is what mediation gives us. It requires counterfactual logic, because the definition of direct and indirect effect involves nested counterfactual. Another tool and a set of application is integrating data from diverse sources. Imagine that you take data from 12 hospitals. Each one is conducted on different types of individuals. Some are volunteers, homeless volunteers, some are rich lawyers, and you want to combine the data that's coming from these 12 sources and come out with an answer to query about a totally different environment that wasn't even in the study. Means of combining diverse sources is now available to us, and algorithms for doing that are now available to us under the category of fusion. Sometimes it's called transportability because it involves transferring knowledge from one area to another, from one population to another. In the machine learning enterprise, they call it transfer learning. But in that enterprise, it is a dilemma, not a solution. Transfer learning has not been successfully tracked, solved in the machine learning area. It is solved in the causal inference arena. Another tools set of application is recovering from missing data. In many cases, participants forget certain happenings. Injured people forget the details of the accident. Sensors are faded, sometimes fading, and so missing data is important in order to, and the question is, can we recover from missing data once we know what data is missing? And the answer is yes, we have a new set of results that tells you exactly when you can recover and when you cannot recover. If you can recover, how? If you can recover, I'll tell you what you need to assume in order to recover and whether or not you have enough information for recovery. So that has been a completed area of discovery, of exploration. The last one is causal discovery, in which attempt to discover the structure of the graph from pure data, making a certain general assumption about the nature of the environment behind the data. If you make them that kind of general assumption, you sometimes can recover the structure of the graph from pure graph, and sometimes you cannot. So you get an answer, yes, I can, or yes, I can't. And nothing, and now I'm coming to 8 tool, and this is a personalized decision making. So let me start by describing the difference between personalized decision making and non-personalized decision making. What we have seen so far in most of the analysis, in all decision making applications that have been analyzed by scientists, is using population data to decide about treatment or intervention. What is the difference? Here we are, I'll give you an introduction. What counterfactual analysis permits us to do is to take population data and estimate the probability that a given individual would benefit by a given treatment as opposed to average recovery rate of the subpopulation resembling the individual. That is the difference. How individual will react as opposed to how a subpopulation that resembles individual will react. Totally different question. We want the former and not the latter. Here's how it looks mathematically. We call it probability of necessary and sufficient, PNS. And look what it says. It says here like that. Look, condition everything on the characteristics of the individual U. Mr. U, he has certain characteristics, age, gender, family history, income, condition on them. But then what you are looking is probability that the outcome would be one, had the treatment being one, and simultaneously the outcome would be 0 had the treatment not been one, which means had he taken a different treatment. That is what we mean by individual response. The focus should be on the end here. It's a conjunction between two things that cannot be observed at the same time. Individual respond to treatment and individual respond to non-treatment or denial of treatment. Right? Simultaneously, that is an entity that can only be articulated in the notation of counterfactual, not in probability and not in even not even in the language of experimental out experimental science. Compare it to what we normally do. We're taking the average treatment effect. What it means, we also condition on all the characteristics of the individual, but this is conditioned on once we have this subpopulation of people that resemble the individual, what do we ask about this subpopulation? We say, find how the subpopulation will react under treatment and subtract the response of the same subpopulation, yeah, under no treatment. Okay? That is you can run the two subpopulations separately. You actually take, in reality, you take two different subpopulations of the same nature, all conditioned on the characteristic that resemble the individual, and you subtract this average from this average. So this is not the case when you talk about personal decision making. Here you're taking an individual and you're asking a conjunction of had the treatment been given versus and simultaneously had the treatment not been given. I'll give you an exact and I ask you to imagine the difference between the two will be clear if you just ask the following question. Suppose you have a randomized treatment trial, a randomized control trial, and you find out that both treatment and control give you the same response. Now we have two competing effects. Two competing models. One says that the treatment has no effect on any individual. The other says that the treatment kills 10% and cure 10%. The randomized trial will not tell you the difference between two models. But as far as the individual is concerned, these are two vastly different models. One that has no effect on any individual, and one that it kills 10% and cure another 10%. Can you tell the difference between the two? Not in the experimental setup, but the counterfactual will tell you, yes, here you have a 10% probability that the individual will benefit from it with it, and sometimes, the outcome will be 1 and will be 0, which means there is a benefit of 10%. For other individuals, you will find that this will be individual will be killed under treatment and cured if not given the treatment. That would be called harm. Okay? So PNS revealed this difference. 8 does not. Now that we understand what the difference is between individualized response or individual probability or individual decision making, let's go and see what we can do with it. How personal decision making is estimated. The PNS is not identifiable in general, but it can be bounded given two different sources of data. If the bound improve, if you have to take a combination of both experimental and observational data, it may even become point estimate under certain combination, and becoming narrow and narrow when we have more information. And that has been our occupation in the past year, to narrow the bound as much as possible. Why combining experimental and observational studies are helpful, even with no modeling assumption, is because observational studies tells you something about the individual behavior that experimental studies do not. It tells you the idiosyncratic reasoning that separate one individual from another. The individual is free to choose treatment by choice, by whims. These whims dictate something that is unique to that individual, idiosyncratic to individual, something that you don't see in the experimental studies. And you don't need a model for that. The results in the personalized decision-making tools will be independent on the modeling assumptions. You don't need a graph. On the contrary, the more confounding you have, the better your results, or the better with the observation, the more information the observational studies will provide as opposed to experimental. So the application are now the following. Typical application is screen drugs by benefit and harm criterion, not by average treatment. Screen subpopulation. Oh, I repeat myself, didn't I? Oh, here we screen treatments, and here we screen subpopulation given treatment. So we know which population to encourage and which population to shun from a given treatment. And the last one, we can match drugs to subpopulation when we're talking about medical applications. When you're talking to business application, it has to do everything that I say about patients, you can translate to clients or potential buyers. Take the example, the problem of selecting patients in need. Hospital beds are a scarce resource, and we would like to admit patients to hospital that could benefit from the treatment given in the hospital. We don't want to get in people who would be cured anyhow, or people who are doomed to die anyhow, which are already terminal no matter how you treat them. We want to select those people who would benefit if treated and be harmed if not treated. And that is exactly what PNS specifies here, as I said before. And if we get both experimental and observational studies, we provide informative bound on PNS. This gives you the possibility to make a decision based on situation-specific characteristics in various areas. For instance, in personalized medicine, for instance, identify customers worthy of offer, special offer, or campaign, or recommendation. In the business world, in the political science arena, characterize the voters who are swayable by a given slogan or by a given campaign. Okay? In general, we call it a unit selection problem. Is a paper written by Lee Muller and myself in 2021. You're welcome to look at it. And I'll give you a more vivid example as we are looking to a specific situation. Imagine that you have now survival data coming from experimental study. So, and here are the difference between female in pink and male in blue. What we find here, survival is greater under drug than under no drugs. Okay, so there is a benefit here of the drug that shows in greater survival rate in both female and male. they look identical. 48% survive with the drug, only 21% survive with no drug, both for female and for male. They are indistinguishable. Now, if we incorporate observational data together with experimental data, you get totally different behavior. What do I mean by observational data? You observe or you take a record of how people behave under free choice conditions when they are given a chance to take a drug or not take a drug. Any freedom, total freedom. You can rely on your cousin's rumors. You can rely on the family history. Whatever, we can rely on what you learn in text or what your doctor recommends. But you have a free choice to decide if you want to take the drug and not, given what you feel about yourself. So this is the additional information that comes from non-experimental data. Look how different these two bar set of 4 bars looks. Suddenly we find that female behave differently. The benefit, but the reason that we have here a difference between drug and not drug is translated to benefit to that many women. And there's no harm. Whereas for men, we find that 21% of them are in the harm group, will be killed by the treatment. They will survive if not treated and killed if treated. And the reason we saw benefit in the experimental data is because the reason we saw a difference here in the average treatment effect is because so many of them benefit. So the difference between the benefit and the harm gives you what you see in the experimental data, but you don't see the individual benefit and the harm. So look at the difference between male and female. For female, we can say you have that 28% of benefiting from it and 0% to be harmed from it. Men, however, should be cautious because you have that many percent of being killed by the treatment. Now, the decision maker must decide between these two competing pieces of information, between benefit and harm. And the way we do it, when you have a decision of that moral question, moral conflict question, we have to assign societal cost to each one of the decision that you make. How do we do that? We go to this chart and we look at the 4 types of individual that can exist under binary treatment. Those that benefit, those that are harmed, those that are totally immune to the treatment, and those who are doomed to die. Those are immune, so it means they will recover with or without treatment. Those are doomed. There are only 4 types of individuals because there are only 4 binary functions between 2 inputs and 2 outputs. And therefore, these are the sum total of all types of individual we can expect. And here we can quantify the percentage of individuals in each of the types: benefiters, harmed, immune, and doomed. And they are different between male and female. We can characterize, we can compute the probability in each one of the type. And now to make a decision, we need to have 4 parameters elicited from the decision maker or the policy maker. I call them alpha, beta, gamma, delta. Alpha is the cost of treating an individual in each who would benefit. For benefit, we have negative costs. We have positive utility, but negative costs. So we assign alpha to these two individuals. This is the cost of treating an individual who will benefit from the treatment. We assign beta, which is the cost of harming an individual. And this cost can be immense, because if you have an autopsy which uncovered negligence of the hospital, the family of the deceased can sue the hospital, and the credibility of the entire medical establishment can be tarnished. Therefore, a decision maker, a policy maker, should decide what is the society cost associated with the risk of harming an individual. And then you assign the cost of treating a person who would recover anyhow. Okay? That eye. Okay? There is still a cost there. You're spending the resources of the hospital on a person which would have been recovered anyhow. Finally, the delta is the cost of treating someone who is doomed, somebody who will be died no matter what treatment he or she gets. Okay? Once you have these four parameters, again given from the judgment of a policymaker, you multiply them by the probability of belonging to these types, and then you compute the expected utility of the treatment. And that is how you decide between treatment, if you have a choice, or between individuals, whether or not an individual should be selected for a given treatment. I think I came to the end of my talk here with this beautiful error networks, and I will only summarize it, what I've said so far, in a quote that was articulated by Gary King from Harvard in 2014, that more has been learned about causal inference in the last few decades than the sum total of everything that had been learned about it in all prior recorded history. And why is that? Because we didn't have a language in prior history to capture the idea that X causes Y, as opposed to X associated with Y, or that the prayer of A is equal to Y or constant times Y. And I contrasted with a slogan of my own and say that the next revolution will be even more impactful once we realize that data science is the science of interpreting reality, not of summarizing data, which means once we realize that we have to climb on ladder rung number 2 and then rung number 3, not to get stuck in the rung number 1, which is normally what you find in the machine learning and the statistics. So I'll end with the advertisement to the Book of Why, which I'm sure many of you had a chance to read, and I highly recommend. Thank you very much for being such tolerant listeners.
Thank you for joining the inaugural Causal Inference Symposium, which was hosted and organized by BP. I wanted to do a little recap about the amazing sessions that we had today. We started off our day with Judea, where we learned about the fundamentals of causal inference. And we also got some insights on how causal inference really can benefit personalized decision-making. Judea's talk was followed by Totte. He talked to us through an important topic of justified assumptions. And this is really key for practical applications of causal inference. Now, it is a very important topic, but unfortunately very much overlooked. So I was really happy that Totte picked this as a topic for us today. That was followed then by Robert, and he talked about ways to use large language models to build causal DAGs. And then Robert also took us through several practical examples. Subsequently, Ben covered Bayesian causal inference and really showed how Bayesian approaches can help by adding uncertainty quantification, which we also heard later just now in the very invigorating panel discussion. Now, Ben believes that in the future, we can pair much more causal and Bayesian approaches. John walked us through various causal machine learning methods and also covered a range of causal ML open source tools, as well as, of course, some great applications to which these methods apply in practice. And we just finished hearing such a great panel discussion between Candice, Lars, and Harsha, covering a range of different topics around causal inference and also AI ethics. I wanted to also highlight that we are recruiting at BP. We're looking for super talented AI, machine learning experts, and of course, causal inference experts to work with us and build solutions that keep our people safe, engage our customers, and accelerate us towards our net zero ambition and solving the energy trilemma, making sure that we have safe, sustainable, and affordable energy across the globe. So if you're interested in joining us, please look at the current vacancies, which you can find on the homepage of this event portal, or also on our careers website on bp.com. We have, as I mentioned earlier, artificial intelligence, data science, statistics, obviously also software engineering, data engineering, and various other positions available across various different levels, as well as regions. And finally, thank you. Thank you to all of the speakers, Natalia, a phenomenal moderator, as well as the producers, and thank you very much for joining us. I'm looking forward to seeing you all at the very next event. Have a great rest of your day.